You are currently the only person in this conference.
Hey, good afternoon, everyone. I'm Anita, and this is Luca, and we'll be running the Service Management and Systemd Micro Conference today. Just some quick announcements before we begin. Thank you to all of our sponsors, of course. If you would like to ask a question, just raise your hand, and Luca will go around with the Collabora mics. If you are remote, I will be relaying the questions from chat to the room, or you can also do the thing where you unmute and ask your question live. However, if you do that, please wear headphones. Otherwise, we'll get a lot of feedback in the room. Otherwise, enjoy.
Hello, I hope you can hear me. Perfect. So I am Michal Koutny. This is me. I am Michal Koutny. I work at SUSE, and I concern myself with C groups, both sides, from the kernel and the user space. And today, I would like to talk with you about a particular problem on the user space side and some proposed solution. So let's get to it. First, some introduction for the background. I see that there are some people who may already be very familiar with this, but for the generic audience, Systemd has some way how the C group hierarchy is structured, and there is one rule called single writer rule that basically says that parts of the hierarchy must have clear owner that is responsible for the configuration of that. And that would mean that because the root C group and all the underneath is managed by systemd, so that would mean that everything is managed by systemd. But it's maybe practical to have some different manager. So there comes the concept of delegation. Here is the quote on the slide. Is a quote from the manual pages that basically explains what the delegation does. That it allows to delegate the subtree to some other entity, and it can manage both the controllers and the processes beneath the delegated subtree. And this applies both to service units and scope units. So here we will start with an example of a service. Here we see by default the delegation is turned off, so the services basically cannot create their own hierarchy or migrate the processes unless they want to confuse systemd. And here in this example, which we start with, we have two processes running of the service. One with the directive exec start, that's the main payload of the service, and then there is some control process that is independent of the life cycle of the service, and it may run in parallel with the payload of the service. So yeah, so and this is how it looks like within the C group hierarchy. We see that both of these processes stay in one C group and they coexist side by side. That's basically what we usually want. In this example, I showed you that there is the exec reload directive, but there are some others that also may coexist with the main payload. Here they are listed. Just note that the first two at the beginning are kind of special because actually they don't coexist with the payload because they run before the main process is started. So they may be thought of that they have everything for themselves. But the others, they have similar requirements like the exec reload in this regard. Now, how it looks like with the delegation from the point of the C group hierarchy. So here we can see the top C group is the delegate control that's created for the service, and then there is the C group subkey control file where I denoted by RW that write access is given to the possible user of the service, so they can modify what controllers are enabled in the subtree. And then we can see there are two C groups created by the service itself for its own purposes. So here it's illustrated by a service that creates one C group for its main payload and second for the some helper running together with it. Yes, this is created by the service. Just to note that there are services, not so rare, that run as a root user. So in theory, they could do anything. They don't need this explicit delegation, but it would just make the thing unorderly, and it would be difficult to get some overview of actually what belongs to what. So in the sense of in the case of root services, this is rather like advisory to delegation. So now we are getting to some of the problems. With the unified hierarchy, there is one thing called internal node constraint. That means that processes can only be placed in the leaf nodes of the C group tree. And if systemd behaved like usually when the control command has to be started together with the service, so it would put it under the main C group. But here is indicated with the 3 exclamation marks, and it would mean that this would not be possible because it violates the internal node constraint. What it violates means that it might not be actually possible to put the process there. So what systemd does currently, it creates a wrapper C group that exists side by side with the custom C groups created by the service, and puts the control process inside it, and everything is fine. Here I want to mention that the internal node constraint does not hold universally, that it can be actually violated when it can be violated in certain situations. Here is an example of a service that may ask for the delegation, it specifies the delegation, but it does not consume this request, and that means that it does not create the hierarchy. You see that the process here is running right under the top C group, but still in the situation, systemd creates the C group, for the wrapper C group for the control command, and it succeeds because the internal node constraint is relaxed in the situation when no controllers are enabled. And that's actually the reason for the internal node constraint. I will get to that later. The reason is related to controllers. Now, now the example is getting slightly more complex. Yeah, here I just changed the name of the service to RT, meaning that it has some real-time requirements. And now it has 2 parts of its payload. One is a sensitive one, second is auxiliary one. And the sensitive one specifies the 2 CPUs that it wants to use for its threads. Here I talk about threads. Those would be some threads with real-time priority. And the auxiliary has the 1 remaining CPU. So this is not so much different from the previous example, still the delegated sub-tree. And now you've heard that we are doing something with threads. So the unified hierarchy is slightly different when it comes to threads. The reason is now it comes to it that there are some controllers that support threading and some controllers that don't support threading. For example, the memory controller cannot support threads well because the whole memory space is shared by the threads, and it would make no big sense to manage individual threads of one memory space independently. So we have threaded and non-threaded controllers, and basically the non-threaded controllers remain enabled in the C group tree in the higher levels of the hierarchy. We would call such C groups that they are domain they are domain for the resource. So they are domain threaded in this picture. And the threaded mode is enabled only in the C groups that are below it. And for these C groups, only controllers that support threading can be enabled. And these C groups are explicitly marked as a threaded type, so that individual threads can be migrated independently. So we have this was the service as was mentioned previously, but there is a slight issue with this, that when systemd wants to start the control command as it is used to, so actually the control, the wrapper C group that's created has by default type that's invalid because it was not explicitly switched to the threaded mode. So the process of spawning the control command fails because it cannot be migrated to this C group which has invalid type. And also, this is a good example to also illustrate another problem, that if we somehow solve the threaded problem for the controls group, it's well illustrated with such resources like the CPUs, which is a resource that's not elastic, I would say, that we have to fit both the original payload and the control command together under one C group. So here, like we've reserved some CPUs for the whole service, but then the question is the control C group, which CPUs actually it should use, and what happens with the guarantees for the rest of the service. Like this is the extreme case of CPUs because of some other resources, which I would call they are elastic, for example, like the memory, so it can somehow fit into that and compromise, for example, the latencies. So this was the motivation examples, and now here is a proposal of some solution that I was looking into, and it's actually rather simple. There is a new directive. The name is just added for the demonstration. There is there's 2 times the word control, which means like in which control group we put the control process. And it allows explicitly specifying both the C group for the control processes and for the payload processes. We have the main, from the initial example, we have the server command, the reload command, and we see that in this case, when it's so configured, the payload would be in its explicit C group, and we can move control command to its own C group. The default here expressed in this syntax is basically what is currently possible. That is that control commands reside in the control C group, and the payload remains under the top C group. But it can be specified. The payload wrapper can be specified, and also I was talking about the threaded mode. So when it's necessary, the control commands C group is switched to the threaded mode, so that the control command can be put into it and it's not invalid. Yes. So there's, for the reference, there is a pull request number. So this was the presentation of the solution. Here is an example and how it can be used. For example, for the currently existing user instance service that's shipped with systemd. And we can see that the original is a start command that starts the user instance, and currently there is no exec reload command, and we could specify that it runs in the init scope. But here in this example, it means that it runs in the init scope under the systemd user instance. So it's somehow put together with the main service of the subtree. There are some other approaches that may come to mind. One of them would be to have a fixed C groups for such a delegated subtrees, where we would separate the payload and control commands every time. That would look like at the first snippet. Or another option would be to put every control command under the global scope, perhaps of the systemd. But all these two, they look more weirder to me. And I also considered a variant where we would just keep things as they are and somehow enable the threaded, somehow created a switch or directive for enabling the threaded delegation, but actually the threaded mode cannot be controlled on the level of file permissions, for example. It just can have, if the if the subtree has the permissions to create a C group, then they can switch it to the threaded mode. So actually, I think that wouldn't work well. Okay, we are getting now to the discussion section where there are some. Okay, here are some points that are worth discussing possibly, or yes, time for questions. Time for questions.
So, one, two. So, when I'm listening to this, it is important to distinguish advisory stuff, like what is a good idea, from what you enforce. And we had this idea of a single kernel, single writer enforced by the kernel, and we dumped it because it didn't prove useful. Now, the kernel is enforcing this no parallel threads, parallel processes, and C groups idea. And I mean, I know it is a good idea in general because you can do accounting cleanly, but also we are building ever more elaborate workarounds. So maybe instead the solution is to just drop this in the kernel and simplify the user space.
So that I'm not sure which.
The kernel should allow this semi-invalid hierarchy, and it will just do the best resource management that it can in this setup. And if you want to have really good resource management, then you do a clean setup. And the kernel just allows everything because it already has to do this for the root C group. So it could just allow it for other C groups.
But
okay,
I mean, it's still our responsibility to provide an execution environment for services so that they can do this cleanly. And right now they can't, right? Like, because you turn on delegation and specify exec reload, and we end up creating something for you that is just bullshit, that is not clean. And that's our responsibility. So we should fix that in systemly.
Yeah, also the comment to the root C group, because that's how it was with C groups v1. So it's kernel somehow must have supported. But the example, for example, of the root C group, so with typical layout of C group tree, so there would be only kernel threads in the root C group. So I don't say that. What I want to say is that actually it's not well tested how it behaves if there were some processes in the root C group with their memory competing with some children C groups. So I think it's better not to go back to the v1 ways in this regard. Yeah.
I mean, if other people want to ask questions, then please go ahead. Otherwise, I can respond. But so when the system with the machine boots, you still have this situation where you have, well, no hierarchy, so everything is in the root, right?
Yes.
And then you start creating subgroups and move things there. I don't know. It seems to me that we could just provide a good enough environment. Sometimes we just don't care about the details of the accounting, and this would just make things simpler.
So what I find interesting about this always is, like, you know, the recommended workflow for delegated services is that the first thing they do is they move themselves somewhere else, right? This is what, like, can you go to the example, like, yeah, the system-user one. The system-user one. Yeah, so I mean, this, like, you explicitly list your delegate control group init.scope, right? Init.scope is a C group that PID1 moves itself to, and system-user moves itself to. So what I wonder about is, so you're already specifying where the stuff shall be put. Why limit that to the control stuff? Maybe we should just have a setting like default control group or something like this, or sub control group or something, which specifies for any process that systemd invokes, regardless if it's a main process of a service or reload or whatever else, where it should be placed, right? And then it's a sub C group of the service C group, because that would solve the problem and at the same time make things less stupid that we always invoke a process that immediately needs to itself move somewhere else. I mean, Christian added for us support that we can fork off processes these days into a C group, right? So that the stuff is never even accounted to the wrong C group, right? We currently don't make use of this for some reasons because glibc and stuff, but it's kind of stupid that we then immediately break this because we require all the delegated payloads to immediately move them somewhere else, right? So it appears to me by doing this approach, but making it a little bit more generic, that we just say default control group or sub-C control group, and it applies to all of them instead of just the control ones. You not only solved your problem, but you solved the other problem as well, that everybody needs to move themselves first.
Yeah, my comment to that would be that still I think we have to differentiate between the control commands and the main command, because we rely on the main command that it creates the sub-hierarchy. So we need...
But it's, I mean, the design of PID1 right now is that itself, it lives in init bus scope and it manages the hierarchy one up, right? And this is kind of what I would then do here as well. Like, it's fully systematic. Like, systemd-user gets spawned in a child C group, and it manages the level one up of that.
But Lennart, what happens if if you go back to the example where this CPU is the sensitive CPU one, that example? Yeah, so like here, if you were to have the ability to say default control group is blah, where would the control group go? Would it go into, because...
But this is like, I mean, in the model that I was suggesting, that we just allow specifying the default C group where systemd puts stuff, then of course there would be no .control, but there would only be like the one where the main stuff is or something like this. And then it's up to the service to set CPUs on that thing, and it has full control, like which CPU it wants to assign that.
Right, but if it wanted to do the same split where it has one sensitive, one auxiliary, and then control gets put into whatever
like, if I see this, like which one is the main process? It doesn't, like, this example doesn't even show us anything that would be the main process, but which one is the management process, if you so will.
Okay.
Let's say a thread 1 is the management process, right? I mean, it's badly named, but anyway. Yeah. That would only be natural, but if the management process in the upper one, then probably also the reload request should go there.
Runs in the sensitive CPU.
Yeah, I mean, it's a bad example, but yeah.
No.
So to follow up on Lennart's idea, if we allow this, then I think we should also allow specifying a whole hierarchy of C groups to be built for the unit, so that the unit can only deal with moving processes around and not setting anything up.
Well, but MKDir is not that hard. I don't know.
No, but you need to deal with supported and not supported controllers and this and that, and just make it easy.
But usually it's dynamic, right? Like systemd-user itself, it creates C groups now and then and under varying names. So it's not a fixed hierarchy, a sub-hierarchy. It's the most dynamic thing in the world, right? With the exception of init.scope, which always exists.
But if we allow it to be
so
very
you need
simple,
like a pre-start. So you need like pre-exec start, systemd temp files create with the list of all the C groups you need, right?
well, I think it would just make easier for processes, for services that want to use delegation to use the delegation.
Yeah, and I think this explicit directive would make it easier, because like it works as the default. The default is like the current situation. It adds the support for the threaded mode, and if the service wants to specify something else, if it wants to put all its control processes into specific C group, so they can specify a specific C group. And also, just I didn't mention it, but I think this is similar to what containers perhaps sometimes have to tackle, that there is some kind of exec command that allows to join a container and run a command inside the container, and this works in V1 hierarchy, but in V2 it would violate the internal node constraint.
Hello? There is a workaround for this, because like this control mechanism, basically, when you attach to a container, you set whatever it is, you set an S to the C group namespace. I think in any way you need to some sort of dance where you try to first, you join a container, you try to join the C group of the container's init process at first, which doesn't work because, for example, it gives you ebusy or whatever it is, and then because you violate the internal.
But if there is init process already, so you can join it. I think there is the problem if you want to
So
join the root.
PID1 moves
loop.
itself into init.scope, right? So what we usually try to do now is we try to join the root C group of the container, and if that fails because of ebusy, then we try to look for init.scope, which is the one that systemd, and then we join that, which is there for some reason. I think we first need to try and join the root C group, or we do, because sometimes, for example, if you don't have systemd, you have OpenRC or whatever, then it will usually work.
But why can't you just always go for PID1?
Sorry, Leonard. If you'd like to continue this discussion, you're free to go to an empty room on this floor and keep going. But unfortunately, we have 4 more talks to go through today. So.
Okay, thank you.
From memory.
One, two. Can you hear me? Okay. Okay, perfect. Thanks. So, hello everyone. Thanks for being here. My name is Babis. I work for AWS, in particular in the Firecracker team. And the talk today is about snapshot safety and work that we and the community has been doing in order to try to restore uniqueness in virtual machine snapshots, virtual machine clones. And that doesn't work, or it does. Okay, yeah, that's right. So I'd like to start by actually defining the problem. So I would like to speak about what do we mean by restoring uniqueness in snapshots, what is the uniqueness that we are referring to in particular, and why do we lose it? Why do we need to restore it in the first place? And let's think about a simple example where you have a virtual machine that it runs on top of some hypervisor, and inside that machine, in the address space of that machine, you have some data, some state that for the purposes of your application, it has to be unique. It cannot be replicated, otherwise it doesn't work, okay? And now suddenly you decide to take a snapshot of that virtual machine. And you might want to do that because you want a backup of that VM, or because you run a service inside that VM and you want to scale out, or because you want to have a snapshot from which in the future you can spawn VMs very fast in order to avoid long latency in cold boots. And then, in fact, you take that snapshot, you start another VM or more of them, and suddenly that property that you wanted at the very beginning, that this object is unique, it doesn't hold anymore. Every single VM that was booted from that snapshot has a copy of that object. And why is that a problem? So imagine, for example, that with every new VM that we spawned before, the state of the random number generator of the initial virtual machine has been duplicated. So now applications that get random bits from that random number generator, they're going to get the exact same random bits in every single clone of that VM, at least until when a new reseed event is coming, you have new entropy. And that is true for kernel space random number generators or user space as well, like the ones implemented using libraries like OpenSSL or language runtimes that implement their own random number generators like Java. But the problem is more general. It's not about random number generators only. It's about any kind of application that uses some data that it considers unique. So, for example, you have a service that uses a certificate to identify itself with the outer world, and that gets snapshotted, restored in many other VMs, and now the service in every one of those VMs tries to identify themselves using that certificate. And any other example like that, like you have an application that tries to write something in a database using an index that it considers to be unique, and suddenly that is not unique. So you have many applications trying to write in that database using the same index, and this can cause a lot of problems, obviously. So this is a real-world problem. It becomes more and more relevant, especially as we see VMs being used increasingly in the cloud in order to isolate workloads. It does affect both kernel and user space, and we believe that there is a need for a generic solution, system-wide solution, and instead of having ad hoc solutions implemented in various systems separately. So then the next of the presentation, I want to speak about the current Linux landscape. What mechanisms do we have today to mitigate the issue? Then I would like to focus a bit more in user space applications to see what kind of mechanisms do we provide to those, if any, to protect themselves against the problem. And finally, I'd like to take a more wider look into the problem, to look at it from a system-wide perspective. So the main, if not only, mechanism that exists today that tries to mitigate the problem, it's called Virtual Machine Generation ID, and it's an emulated device that was introduced from Microsoft more than 10 years ago, I think, exactly to solve this problem. So the way this works is that it exposes a generation ID inside the guest. That generation ID is a cryptographically random 16 bytes integer. And that integer, the value of that integer changes every time the machine executes from a different configuration as per the specification. Essentially, what that means is that every time you take a snapshot of the VM or you start a new VM from a snapshot file, that value should change. And that should let the guest know that something happened with the VM. So the mechanism works, one, as a notification for VM lifecycle events, and two, the value itself being a cryptographically random number, it can be used as a source of entropy for inside the guest. Yeah, and it's defined as an ACPI device. So Linux recently implemented upstream support in the main line for VM Gen ID as an ACPI driver that maps the generation ID in kernel memory space and handling ACPI notifications, which they arrive every time the generation ID changes. Essentially, the way this works is that at some point, the hypervisor receives a command to do something with a VM, take a snapshot or restore from a snapshot. And at that point, the VM is paused. The vCPUs are not running. The hypervisor updates the value of the generation ID, injects inside the guest the ACPI notification, and resumes the vCPUs. Now, the kernel at some point will handle that ACPI notification. It will read the new value of the generation ID, and if that is not the same as the old one, it's going to use the new value to receive its internal random number generator. It's going to use it as randomness. And that has the effect that applications that call now get random to get some random bits from the RNG, they can feel sure that other clones of that VM that has started from the same snapshot are not going to receive the exact same random bit. So the unpredictability of the random number generator is preserved. A very important note here is that this whole workflow that I described, it does include a small raise window, which it is there because of the asynchronous nature of handling ACPI notifications. Essentially, what that means is that if an application calls get random before the kernel handles the notification, it's going to receive random data using the old state of the RNG. But the implementation so far assumed that this window is very, very small, and it was the best thing we could do at the moment, probably. Or at least it was considered to be. Apart from that, there is the question of user space random number generators. They have the exact same problem as the kernel implementation, but the virtual machine generation ID does not provide by itself any mechanism in order to let the user space know that something happened with a virtual machine. So another application that uses a user space PRNG, it's going to continue to get the same random bits as every other clone of that VM that exists and has started from the same snapshot, again, until new randomness arrives in those RNGs. So that's the main point of this discussion here. We were trying to see what we can do for the user space, what kind of mechanisms we can expose. So the concerns that we have about today about the VMGen ID itself is that first, it does not provide us in Linux with any mechanism for the user space. Second, the generation ID itself, it's consumed from inside the kernel in order to provide entropy for its PRNG. So it has been thought, it was thought that probably it's a security concern to expose it to user space as well. And of course, the race condition we spoke about. And there has been many discussions on with the community trying to address those issues. And one of those discussions follows the line of integrating in the specification, extending the specification in order to add an extra variable, an extra value, which is called the generation counter, which is a word size counter. And its semantics is that it increases every time the value of the generation ID changes. Okay. Now, this is not a source of entropy, so there are no concerns about exposing it to the user space. And the way that it has been foreseen to be used by the user space applications is by it provides, in order to be used by user space applications, it provides an mmap and a poll interface. Also, it has the additional value that it is word size, so it can be read with a single instruction in any given architecture. So going back to our previous example, the way that user space PRNG could use the generation counter is that it could mmap it into its address space, cache it, and every time random bits are requested by it, it could go back to the generation counter, read it, and compare it with the value it has cached. If they are the same, everything is fine. But if not, it means that something has happened with the VM. So it needs to update its state. It needs to reseed itself somehow, probably by calling get random from the kernel or with some sort of entropy. Other applications could use the poll interface. If they have threads and event loops, they could use the poll interface to register, to wait for events, for changes in this generation counter to come. So they know that something has happened and they're going to update themselves. But as I said, this is an open discussion. There are questions to be answered, and the community is looking into alternatives as well, trying to find the best API possible for user space. One of the questions that has come up is that it is true that the generation ID is used for entropy inside the kernel, but it is not clear that it's actually harmful to expose it to the user space. In the sense, the rationale here is that it is secret to that VM. It is not replicated to any other VM. So maybe exposing it to the user space as a source of entropy for user space random number generators, maybe it's not okay. Maybe it's not that big of a problem. Of course, there is no answer here. And if you have opinions, I'm glad to hear them. But if we could do that, and doing that, we could actually use the generation ID as well inside the kernel, the same way we would use the generation counter in order to avoid the race condition in the kernel. Here, the flow would go that instead of waiting for the ACPI notification, the implementation of the kernel RNG would cache the generation ID, and every time get random is called, it would read again the value. And if those do not match, it means that a VM event has happened, and we need to do something. We can use the new generation ID to receive the kernel RNG. Also, the fact that word size reads are faster, it's true, but there have been benchmarks that show that the difference it's of something very, very small. So probably for real world use cases, reading 16 bytes, maybe it's not a problem after all. So another idea would be here to just expose the virtual machine generation ID towards the user space directly without having to extend the specification at all. of course, before doing that, we do need to clarify if that is a security concern in the first place. Okay, now let's assume that we do have a mechanism for the user space in order to be notified about events with a VM. And let's see if that actually solves the problem. So again, going back to the previous example, we have an application that goes get random from the kernel random number generator. The VM here, it has support for VM gen ID. The kernel uses that in order to make sure the RNG, the kernel RNG works fine. Okay. And the application gets some random data and it uses it internally to create some other object. And at that point, it receives a snapshot request. Now, we are in a situation where the data we received from the kernel's PRNG is fine. We, in the sense, fine here has a definition we used before. We are sure that other clones of that VM have not returned deterministically the same exact random bits. Okay, but that object that we created in the application before is now part of the snapshot that we took, and new VMs are going to include it. And of course, this is not a problem it's not an RNG specific problem. Any other application that does something at that point is going to get its state in the snapshot. And even if it has a mechanism from the kernel to figure out that something has happened, think about the scenario where it is actually in the process of writing in a database somewhere remotely, and that operation is in flight. There is nothing we can do. There is nothing we can do to predict that this would have happened. So there is an in-flight operation outside the VM. So that makes us think that VMGenID is a great tool for allowing us to detect world changes, but probably it's not enough. If we wanted to validate that our state hasn't changed, we should do it in every level of the application. So we would need to go and patch every application out there to validate the value of VMGenID or gen counter or whatever, or in every operation it does, in every transaction it does. And even if we did so, there is nothing we can do about operations that are already in flight. And that is because VMGenID-like mechanisms are post-mortem. They allow us to react to events, such as take a snapshot or restore a VM from a snapshot. And probably we should be thinking about stuff that we could do before this event even happens. So essentially, the problem arises from the fact that VM events arrive at arbitrary points in time in which we have no control. And another thing that it seems to be relevant here is that the problem is particularly relevant when our VMs are networked. They communicate with the outer world. If they weren't, they were in a silo, then any sort of secrets would be there and they would not interact with anybody else outside the VM. So following these observations, one potential solution would be to control the timing of snapshot VMs. We should only try to perform these events when it is safe to do so. So for example, when we are not communicating with the outer world, and when we are restoring from a snapshot, we should allow applications to readjust themselves before we consider that the VM is safe to operate normally. For example, restart the network. So, and this is the systemd part of the presentation. So we try to model this in systemd, and that was work that happened like a year ago, more or less. We do that by defining the state of defining 4 states for the VM. When the VM is running, it's business as usual. Everything runs normally, nothing has happened. Now, when you want to transition to a state that is safe to take a snapshot, that is the quiescing state of the VM. Once you have reached that state, you are in the quiesced state. And at that point, it is OK to take a snapshot of the VM. Yeah, sure.
Sorry. With regards to safety, in the quiescing and quiesce state, would that require some kind of a user agent? For example, if you have your file system, you could be snapshotting in an unclear file system state between the snapshot and your parent. Is there any mechanism to prevent that? Would some kind of a user space, or I guess in kernel, tell you when are from the I/O point of view, is it safe to snapshot the file system?
So yes, the idea here is that transitioning from, we wanted to essentially reuse an idea that is already, mechanisms that are already in systemd, which are inhibitor locks, and an application that would need to do something before taking a snapshot, it would get an inhibitor lock, and would not let the system go into a quiesced state until it does whatever it needs to do in order to mark itself as safe for snapshot.
When you say the application, are you talking about the user space QEMU process? Or?
Any service, yeah.
Okay.
So why isn't this, like, you realize that this is what you want is similar to system control suspend, but why isn't it identical to system control suspend? Like, why not send basically the equivalent of a ACPI suspend button pressed event to the VM, then the system suspends, because there's already hooks in all the networking stuff to when you come back from a suspend to re-request a DHCP because your machine might have moved and things like that. So I mean, I think it's unrealistic to get large amounts of user space software to adapt to a new concept, but my question is, the existing suspend concept, isn't that exactly what you need already?
I think that's a discussion we could have. I think we were discussing, you were part of the discussions last year, right?
Yeah, but I forgot all.
I don't know, Alex, do you have any comment on why we cannot use systemctl suspend?
Awesome. In a nutshell, it's a great idea. The main reason why we didn't do it is because the current interface doesn't have it. There is just no ACPI event. There's nothing we can officially inject into the guest to say, please go into a safe state that isn't an S3 or something. We only have actual ACPI snapshot states, like suspend states. We have S3 and S4. Yeah, he's just a second.
Well, I mean, there's certainly an ACPI event to ask for a system suspend, which is traditionally bound to the sleep key of your laptop, right?
Correct.
You could send that thing, and then what happens is what systemd makes of it, and you have these many sleep modes in the kernel. You could just add a new one, and I mean, nothing is hard-coded to S3 there. You could just add a new one, and then if that's the only one that's available, then we just use that one. And then in the kernel, you just do basically nothing.
Yeah, totally doable. I agree.
Just the driver.
It's just, well, and also that's no precedent, but I think the idea is absolutely sound. I think that to invoke that path to say, hey, we do want to go into a state where we want to be safe now, please shut down, in quotes, so that we can then suspend you. I think doing an ACPI event from the outside and just acting on it based on typical existing logic for suspend is exactly the right thing to do. What we do need to make sure of is that on resume, if we're going through the typical suspend path, it's on resume, you still need to enlighten all user space to then go and check whether your generation changed, because you don't want to always reseed every random number, whatever path, on every time you go in from suspend resume, right?
But I mean, like I mean, you list network manager, network D, and things like that. Those all refresh the DHCP releases when they come back from.
They
suspend.
definitely do, yeah. But Samba won't generate a new SID.
Don't use Samba.
Just saying, like one example, one completely arbitrary example.
Really weird to duplicate Samba in the millions on AWS or something.
It's a generic problem you want to solve generically, right? So you need to be able to create some mechanism that allows you to regenerate your UIDs that otherwise would not.
Sure, but it sounds like as if the suspend stuff is kind of what you want, but then you probably should also check I mean, because we tell you when we go down and we tell you when we come up, and then if Samba would then also look at the VM Gen ID, then you're already done.
Exactly, then you have it.
Or you need more hooks, like on resume, you have some script which will poke Samba and force it to do stuff, such that you need more hooks.
Yeah.
So do you expect things like networking to change, like the NIC and the MAC address and stuff to change over the transition, or are you going to do that at some other point?
I'm not sure I got it.
When you resume a new VM,
will
its MAC change?
I think so. It should, right?
I think, I mean, this probably depends on what people want, but in systemd we already have this way how we hash the MAC address for you from some other seed thing, and so we probably could extend that when you choose to do this, that we also include the VM Gen ID in the hash as input, and then basically, yeah, when we come back, we not only re-request the DHCP release, but also update the thing fully automatically, if you follow what I mean. But yeah.
Changing the MAC address on the fly on suspend resume is not going to be trivial, because your device model ideally shouldn't change between a suspend and between both suspend and resume from S3 as well as for normal snapshots. That one's slightly tricky to change the MAC address between the two. Doable, but probably needs driver changes or at least adaptations.
You do that. I know.
Can I jump in here for a second?
S3, I think.
So, I mean, as you go through this and all the various examples, well, MAC address needs to respond one way, like cryptographic keys need to respond another way. You see that like each situation is sort of case by case on what the semantics should be. If you need it to be stable, if you need it to be unique, if it represents a compromise, or if it's just a refreshing, just like the RNG resees itself every 2 minutes, but wasn't necessarily compromised, whereas we assume on a VM fork, it is a compromise. So you have all these things that are case by case, but that all kind of makes me wonder about the motivation for jumping from what you describe as the post-mortem checking to the system-wide snapshot safety, where you gave this example of the transaction that's in progress and what do you do with that. And so like if we start with a user space RNG and say it's using some fancy thing with the VM Gen ID, but then as soon as the number leaves the RNG and is on its way to the consumer, say there's a fork there, well then the whole thing kind of breaks. Like then both forks are going to get the same number. But if you start to consider this in the context, like are you doing crypto or MAC address or whatever, now let's consider the crypto case where you want to avoid using the same nonce with the same key. Otherwise you get some kind of catastrophic key reuse. But it turns out the solution here is that you check the VM Gen ID once before you do anything, that is right before you generate your keys, and then just before you transmit onto the network. And if you do it at those two places, you're fine, then you won't have nonce reuse.
Correct.
And if something changes just after you've transmitted, then you've transmitted the same data in both cases, so you don't have a break. So it seems like for all of these, you wind up with these kind of case-by-case logic that belongs in an application on what the right behavior should be, that trying to encapsulate it with some kind of system-wide snapshot thing, that all the problems rear their head again. All right, well, what do we do about MAC address? What do we do about crypto? I don't see what motivates the shift to wanting to do this in systemd.
Okay.
It seems like you can do everything.
No, but baby, it's not a shift. It's not a shift. It's an addition. So ideally, you want to be able to solve for the normal snapshot restore case. You want to solve 99% of the cases by just having application logic that goes and identifies, hey, I'm in a new world right now. Let me go and process things differently. Whatever way that different means, whether it means reseeding, whether it means changing or renegotiating a current identifier, whatever that is. Where the systemd pieces come in is imagine a world where we no longer boot. We don't boot anymore. Like every Linux image you ever run on a virtual machine environment always starts from a snapshot. Always. In that world, you always will have certain parts where your overall environment assumes uniqueness. Samba is just one case that immediately comes to mind, but there's more pieces here and there.
Why can't you
sprinkled as
just
well.
do that post-mortem where you check the VM gen ID just before you transmit and you make sure that's the same ID as at the time you generated your keys? And if it's different, then you go regenerate your keys.
Oh, you want to, for example, be able to launch. Let me just give you a super simple example. SSH daemon. You want to be able to boot a full Linux system that has an SSH daemon running, but after that snapshot, you kind of want to have a reseeded host key because that should be unique after for a different VM, right? So you want to be able to stop that SSH daemon before you go into this synchronization state, and then once you come back up, regenerate the key or generate a completely new key, and only then start SSH daemon again, and then you can log back in.
But don't you get the same thing doing it post-mortem too? You know, things change. Say you get an asynchronous or racy notification to generate the host key.
You get a.
But in the meantime, if you have requests coming in, they just get dropped naturally.
It won't get dropped. It will get. There's a slim but existent chance that you will get a connection to a stale.
So what I'm suggesting is they get dropped anyway because the VM gen ID counter has changed, and the counter is checked right before you transmit everything on the network.
I really don't like the counter idea because I don't understand what prevents two VMs, two snapshots seeing unique counter values.
They don't have to. You don't care.
You don't have to. They don't have to.
The counter is just to tell you that
be
something changed.
Worldwide unique.
Sorry, a bit loud.
It's an edge notification, like something.
Yes, it's just a
Something
flag.
changed.
Yeah, it's just to tell you something changed. This thing is okay. The one is a little detailed, but you do need to ensure that.
No, on to your mouth.
Okay, that when you pass, when the user space observes the counter changing and does a get random, that the kernel has also observed the counter changing, which in multiprocessor architecture with weak memory access models and whatnot can need to be ensured. And so you really want the PRNG to test after the fact. You can't rely on the SCPI notification at all in the kernel. The kernel get random must do a check of the generation ID after the fact before returning it to user space. Yeah. Otherwise, you again get fantastic race where user space sees a new counter, gets a new random number from, except it's actually the old one.
Yeah, the kernel's got to be.
Yeah.
As you say, you're right. The kernel must be post-mortem. The reason it's not now is simply because the thing we have is 16 bytes and is annoying. But sure, if we add this counter, then that kind of goes away. But I mean, if the kernel can do that, every piece of user space logic can do the same exact thing. Like you were talking about the SSH host key example. Someone connects.
You would basically just say
you're about to reply, but before you do, you send the results of any cryptographic operation. Check to see if the counter's been incremented. If it has, drop it and don't send anything on the network. That is anything you can do here can be converted to the.
So you're suggesting that we should patch every SSH?
The problem is you have a layering violation, right? You provide the host key to SSH. It doesn't know anything about that key suddenly no longer valid because some counter changed somewhere. You know what I mean? The host key comes from a file on a file system from an SSH config somewhere. It's not associated to a counter. It's not associated to anything. So you would have to build into SSH the concept of its configuration that it reads from disk is associated with some kind of counter. You know what I mean? There is a layering violation problem here that is between what's happening in the depth of SSH and all the data such as the host key that it obtains through file system, config files, and whatnot, which need to change, right? So I mean, it's not so in principle what you say is right, but in practice, how you actually implement that seems to me to be quite tricky.
But I mean, is it really that hard? Because everything you actually need to do is just exit, right? so that it gets restarted and can do its key stuff and everything else again, right? Like, so would it really be that hard to add to SSHD that whenever it sends something on the network, does a quick check, and if it
Well,
but I mean, what I would really like to understand, right? Like, we're talking about pre-mortem and post-mortem. Like, which are the use cases you have in mind for the pre-mortem stuff? Like, what is actually the use cases that need to run before? Because I mean, this is what systemd will give you, is the pre-mortem stuff. So
correct,
Yeah.
I agree. If you want to,
The network, right?
network is the big one. It's really just to shut down the network so that you don't even start having, or that you don't have any lingering connections at all anywhere in any of your system. So you would tell them the system. You would tell
so
them
you
on the
actually
network
want that a
and free.
TCP reset is sent out before you do this.
Yes.
Yeah.
Okay, this is your answer then why this actually might make some sense. I'm sure if I agree with this.
Well,
Daniel Barringer here on the remote session. If I can just ask a question, I'm a little concerned that we're using two concepts on top of the VM Gen ID that are perhaps mutually exclusive. But the original purpose of the VM Gen ID stuff was to allow you to detect when a VM has been rolled back, so that you can avoid reusing keys, for example. But in that scenario, you don't want to change your SSH host key. You don't want to change your MAC address. You don't want to change a whole bunch of other things. You want them to stay the same. But it's still the same VM. You just rolled it back to a previous point in time when you're trying to avoid reusing state. And that's quite different from using snapshots from the point of view of forking VMs, where you have now multiple VMs running from the same original source. So I'm just wondering how we distinguish between those two use cases, given we only have one mechanism, which is the VM Gen ID, that's trying to be pushed to handle both.
Comment, I agree, completely agree. The simple answer is the big proposal we have on the table right now is to just extend VM Gen ID with a second counter, and we could literally just call it a fork counter.
I think the question's still relevant, though. We want this counter anyway to be able to do this sort of a race-free postmortem detection.
Yes.
But that's going to come up in the case when you roll back and the case when you fork.
It doesn't have to come up in the case when you roll back.
Why? That's a case when you definitely don't want to repeat the same key stream.
So like you want to renegotiate a client connection key rather than the host key.
Right, exactly.
I see. Ugh. So what would you do?
Give it to Leonard.
Okay, I'm always looking at this from a systemd perspective again.
Yeah.
Like, and you said you want to do the TCP or reset first, but this sounds like a kernel question then, right? Like, you could also just say, yeah, when you initiate the freeze, you just tell the kernel, and the kernel just terminates all TCP connections, and then that problem is solved, right? Like, what do you actually need systemd user space?
Just brings the network down, you mean?
Mm-hmm.
Well, I mean, don't call it bringing the network down. Just terminate all the ongoing transactions, all the TCP connections.
We could do it in the hypervisor as well.
Sorry, it's tricky because again, you want to if you want to regenerate new keys and all of that, you have to put everything on hold for a certain amount of time while you're going to rerun SSH keygen, where you're going to. So it's not just resetting the connection and getting new connections. You actually have to reestablish new states. Which is going to be an asynchronous process. It's going to take a certain amount of time. And during all that time, you don't want the network to start again. So I can understand why going through that systemd process is appealing, because you get all of that for free. While the more low-level approach that you were proposing, sorry, I don't know your name, before, is trickier because yes, it's instantaneous. You know that you may need to drop something, but you don't necessarily know or have the orchestration to synchronize with whatever mechanism will regenerate all the keys and will eventually tell you to restart. And even SSH itself, it's not going to do it.
This is the point. This is basically the same point you made earlier about SSH. All right, you drop the thing, but then you get this layering violation. How's it know it's got to regenerate its keys? And Leonard mentioned, well, you can just like exit and check on the error code or whatever. But the other way is the initial thing I propose is you're checking this synchronously with the counter to make sure you don't do something terrible cryptographically. But then you also have an asynchronous notifier via the pull mechanism that when it gets things asynchronously that is racy, it's after the fact, but it doesn't matter because the race is handled by the synchronous thing. But then you have some daemon that shuts things down, generates new host keys, and does all the rest. But well, this thing is supposed to run pre-mortem before. But what I'm suggesting is you can do everything with just the VM Gen ID situation where you have a file that you can mmap if you want to do the synchronous thing where you're checking, or you can pull on that file to get some asynchronous notification. And so you could have some daemon that's always pulling on that gives you an asynchronous notification post-mortem that it needs to set things up again.
You will still need, so let's take SSH as our example. So SSH detect the change, need to drop everything on the floor, and then you still need something somewhere that will then wait for that other mechanism before you restart, because otherwise you're going to snapshot a new number without having created new keys or whatnot. So it needs to be a one-off thing. It's a circuit breaker. You must not allow SSH to restart operations until the new keys have been generated. So yes, you will detect the change, and you will potentially quit SSHD and whatever. So it's a circuit breaker. Your entire environment, your script, your init script, all of that needs to then fundamentally wait for this asynchronous event before restarting things. So you need a specific error code, for example.
It's simpler design. So for the synchronous checking, SSH's behavior there is just not to transmit things onto the network. Maybe it quits, maybe it doesn't really matter. It just has to stop transmitting. Then you have your other daemon called, restart VM stuff D.
I think it's much easier than that.
Polling,
Jason?
and then that will, then that'll restart things and do whatever.
Jason, I think it's much easier than that. It's if you combine, if we basically conclude that conversation, right? What you're saying is we have two completely distinct cases. One is fork and reseed or regenerate yourself, and the other one is fork and just drop your regenerate your uniqueness, but don't actually regenerate things like host keys. And for those two are policy questions that your administrator needs to do in one of those sequences, which can be a suspend sequence. So what you could do, and I think this is really what I'm hearing from this conversation, is we should be building the VM Gen ID second page interface that allows you to map in a synchronous interface into user space, that allows you to create a poll interface to user space. All of that should be done. Step one. Step two is if we really just go and implement, say, even S3 by all means, just basically going through the normal suspend path and just have a simple hint somewhere, which could even be a file of all things, that says, once you're coming back up, regenerate yourself. We can just go through the existing hooks that systemd already has up when you resume from a suspend, and then just regenerate your keys, because that is an admin inflicted decision anyways.
Sorry, folks, we're at time. We need to give time to the next talk. So thank you very much to the speaker.
Thank you. Hi. Yep. Sorry.
Arrows left and right.
Okay. Do I need to turn it on? No. Okay, thank you. So hi everyone, I'm Dan. I'm work on the Linux user space team at Meta, and I'll be talking about some of the ways we've been trying to improve systemd journald with the goal of adopting it more internally. So a quick overview of the journal. Systemd journald is basically the logging daemon for a system, which I guess everyone knows. The way log messages are structured in journald is a little different from normal or other logging daemons in that it's not just a single message. It's actually a set of key value pairs. So journal message consists out of fields with identifiable names, and they can have whatever value that you want to assign to them. this log message itself is assigned to the message field, but then there's a whole bunch of other fields as well to identify other information, such as the process ID, which service the log message is coming from, and whatever else you want to attach to it. And users can attach their own fields as well for information that's specific to their application. So for example, you could put an HTTP status code in there, or anything else you might want to think of. And the goal is to be able to use this information to then be able to filter the logs later. So you can say, give me all the logs from the service, give me all the logs from the service that have this specific HTTP code attached, or more. Whatever you can think of, really. And then the other thing is that generally the fields don't have a limited size. So theoretically, you can put whatever you want in there. In systemd, we actually put entire core dumps in there, which doesn't always work very well, but you can do it. So to make this work, the journal has a binary format, which is how the messages are stored on disk. And so I'll give a quick overview of how this format is constructed. The requirements that the format needs to fulfill are like the following. So we need to be able to query all messages with a specific field value. That's what we support now. And then there are some questions that I have with that, is that maybe we should also support querying all messages without a specific field value, or with or without a specific field. But these use cases aren't supported yet. So we need to support the large data. We need to be resistant to corruption when we're adding more data to the journal. We need to be able to compress things, because if our fields can be large, then we ideally compress those fields to save on space. And ideally, we should also be space efficient on disk, so that all this extra metadata for logs doesn't cause our logs to blow up in the amount of disk space that they use. To make this work, we have the journal format. So this is an overview of the current journal format. So I'll give a quick overview to hopefully give you an idea of how it works. A journal file consists out of a list of objects, and the objects can be variable size and they have an assigned type. And so we have a bunch of object file types to make the entire thing work. The most basic thing we need is an object to store our log message. This is the entry object. So this is basically an object that stores a single journal message. So it has some general information like a timestamp, monotonic end real time, an object header for some extra information, the boot ID of the current boot, and some more. And then it stores the actual log messages, key values themselves. Now, if we just stored every field directly inside each log entry, we would end up with quite some disk space usage, because every field can be large. So if we duplicate it across every log message when it's used multiple times, we end up with a huge amount of disk space usage. So what does the journal do to address this? Fields are deduplicated. So an entry object doesn't store the field itself. It stores a reference to a data object, and the data object contains the actual field. If a field is used multiple times with the same value, they all point to the same data object, and you only need to store the actual field once. Then we need a way to iterate over all the entry objects that we create for each log message. For example, if you want to grab the log message, you need to be able to iterate over all your log messages. So over all the entry objects, for that you have the entry array objects. An entry array basically stores a list of offsets to entry objects so that you can iterate over them. And an entry array object is really a linked list, in that you can, whenever the current entry array object is full, you allocate a new one, you patch it into the previous one, and your entry array is extended. So then we also need to support being able to quickly find all the entry or log messages that have a specific field with a specific value. For that, the data objects also have their own entry array, so that and in that entry array, all the entries are stored that have that specific field value. So you can just go to the data object, iterate over its entry array, and that will give you all the log messages that have that specific field with that specific value. For example, the HTTP status code again. So that gives you an easy way to get access to all those messages, and also a fast way. Of course, we need to be able to find these data objects in the journal file. How do we find those? Well, we use a hash table. So that's where the hash table objects are for. So you basically go to the hash table and you hash your input, and then you can find the data object that you need, and then you can iterate over the entry array in there. Then we also need to support getting all the unique fields, unique values for a field. So for that, we have field objects. They also have like a pointer to all the data objects with that specific field. It's also a linked list, so that you can iterate over those again. And then there's also a header object, which is at the beginning of the file, and it just contains general information about the journal file and pointers to all the other interesting objects. So from the file header, you can get to the hash tables, you can get to the global entry array, you can get to the end of the file if you need to append stuff. And that's more or less a very quick overview of the journal binary format. So there's a few problems with this format. One thing is that if you use it as is, you still end up with a file size that is much larger than the equivalent plain text log, which kind of makes sense because you're not just putting log messages in there, you're putting a whole bunch of extra metadata in there as well. So while we do deduplicate all those fields, so we don't duplicate the fields completely, but we're still storing a bunch of extra offsets to those fields. And so if you have like 20 fields per log message, and each of those offset takes 8 bytes, then you end up with 120 or 160, I actually miscalculated there, bytes per entry of overhead. And that actually is an overhead that is larger than a short log message. So that's where you end up with like a huge amount of extra disk space, because you have to store all those offsets along with the entry. Another problem is that grabbing is actually quite slow in the journal, but we're not going to discuss that further in this talk. It's also probably, I haven't profiled it yet, but it's also probably caused by just the amount of extra data that's in the file. So I've tried to do a few optimizations to this format in order to improve the situation. And I'll go over a few of these right now. The first thing was probably the most obvious one. So all the offsets are stored as 64-bit in the journal file. And the idea was, if we limit the journal file size to just what can fit into a 32-bit integer, then we can reduce the size of all the offsets to 32-bit. So I implemented this and for a few specific object types, because it wasn't exactly easy to do it all at the same time, because the way the journal format works is it is M-mapped. So to be able to support both the old versions of the format and the new versions of the format, it's actually quite complicated to do when you're using mmap to access the journal file. So we did it for a few journal fields where it was actually easy to change. And this, you can see some results. This is not for every offset, but for, I think, only the entry arrays, where we changed from 64-bit to 32-bit. And we immediately got a reduction in file size for about 500 megabytes by doing that. The limitation is that we limit our journal file size to 4 gigabytes. Then we have relative entry segnums. So each entry object has a sequence number assigned, also 64-bit. And we can easily limit that to 32-bit, because a journal file is not going to have billions of entry objects. So we don't need it to be 64-bit. We can make it 32-bit. Then probably the most significant addition was to use a tree to store the offsets in each entry object. So the observation we can make is that for a lot of the log messages that we're logging, aside from the log message itself, all the rest of the fields are probably, not entirely, but a lot of them are going to be the same. Like every log message from a service is going to have the same process ID, for example. And a lot of the other fields that are added by journald itself are always going to be the same. So instead of duplicating all those offsets in the entry object each time, we can store the offsets in a tree. And that means if we are using exactly the same fields aside from the message as another log message, we only need to store one extra offset instead of 20 extra offsets, for example. So I actually made another diagram for this one to see how it looks in the new format, which we call the compact mode, by the way. So we can basically see the entry objects. They don't contain the offsets themselves anymore. They contain a pointer to the tree nodes, leaf nodes for their specific offset. And so the way it works is when we get a new entry object, we sort all the offsets to the data objects, and then we find the longest branch in the tree that matches all those offsets. And if there's any that don't match yet, we append more nodes to the tree until it contains all our offsets. And then the leaf offset, we store that in the entry object to make everything work. We also need to be able to look up these tree nodes easily so that we can, for when we're appending, that it's actually fast. And so we also have a hash table so that we can find the tree nodes easily. And the key there is we basically take the hashes of all the fields and then we sort them together, and that we can use as a lookup into the hash table tree. I think I have forgotten to put the results of that in here. That's my bad. But this was by far the most significant optimization. I think it was about 800 megabytes from 2.4G to 1.6G just by using this. The disadvantage here is that when you're actually looping over your journal file, you're not just when you're accessing an array anymore to access your offsets that point to your data objects, but instead you have an extra indirect jump to the tree nodes in there before you can actually access your field. So I haven't profiled this yet, but I don't. There is like extra logic involved there to finally get to your data object that you're looking for, compared to before. Oh, I did. Oh, so my bad. Yeah. So like I said, 800 megabytes of savings. So then there was, this is not size optimization. This is an optimization to make appending to the journal file quicker. So usually when we're appending to an entry array, we start at the front and we have to loop all the way to the back. So remember that an entry array chain is basically a linked list. So we start at the front of the list and we have to go to the back. That actually ends up taking quite a bit of time. So what we can simply do is we cache the final entry array object in the linked list so that we can jump to it immediately instead of having to iterate from start to finish. And by doing that, we can reduce the time required to copy a 4G journal to compact mode in the compact mode in almost by half. So that was another nice optimization to find. This does end up taking a little bit of extra space in the journal file. But given the speed up, I think that's probably worth it. And another one is adding a little bit more configuration to exactly what we store in the journal. So by default, the journal stores all the fields that you give it, and journal itself appends quite a bit of fields like the process ID, the service, and a bunch of other stuff. And so, sorry, this is about the, so what can we do? We can say all of these fields are indexed. So what can we say? Like maybe we don't need some of these fields. Like for example, there's fields, I think for SE Linux stuff, there's a field, and there's some other capabilities related fields. And what if we can say maybe we're not interested in these fields? Let's not index them. And this basically means that for that data object, for that field, we don't have to allocate the entry array that allows us to quickly iterate over all the log entries that have that specific field value. And so if we say don't index it, we don't need that entry array, and we save space. And this, again, with a bunch of fields disabled, also gave it another 400 megabytes win. The downside is, of course, that you can't index on those fields anymore. So if you end up with a field that you do actually need, then yeah, you're in trouble because you lose that information. So in this case, there's a trade-off to be made. You need to figure out which fields are actually important for you and which ones are not, and then configure them using the environment variable to actually get the savings out of it. And then there was configurable field deduplication. And so this is about the data objects. The data objects themselves, they do take up a bit of extra space, and they only really help if a field is used multiple times. So because then you only benefit from the deduplication. If your field value is unique, then you don't gain anything from the data object because you're adding a bunch of extra stuff without really benefiting from the deduplication that it provides. And a very good example of this is the log messages themselves. While they do get reused sometimes, often a log message is going to be unique because there's going to be, like, I don't know, a file size in there or whatever, or an error that doesn't repeat itself. And that means you're allocating a data object, but you're not doing any deduplication. And so what I implemented was a way to store the unique field values into the log entry itself, which means that you're not allocating a data object. And that way you can save more space. This one didn't do as much. So this was on top of all the other optimizations already, but we still ended up with a 200 megabytes file savings to implement this. Note that by doing this, you really imply the non-indexing as well, because to be able to do the indexing, you need a data object. So if you don't even have the data object, you can't do the indexing either. Then there's some things that I haven't had time to implement yet, but that I've thought might also be useful. So the first thing is using dictionary compression for what we use the tree now. So the idea is that if we're archiving a journal file, which is when we're done writing to it and we're never going to write to it again, instead of doing the tree, we could also build a ZSTD dictionary for the object offsets that we were storing in the tree and simply compress them and decompress them when we access them. And that might be able to give the same amount of savings as a tree or something close to it, but it would still allow us to, maybe allow us to have to jump around less in the journal file to actually access the data objects. Because if you decompress the compressed offsets, you just get an array again. You don't need to jump around all the file in order to find the data object. You have a direct link instead of having to go up a tree. But then that does mean that when we do archive the journal file, we have to basically rewrite it from scratch in order to get rid of the tree and add the dictionary compression. So that would be probably a quite invasive change. And then another thing is if we decide to rewrite the journal files when we do the archiving, the other thing we could do is we could take all the entry arrays that are now a linked list. But we don't need the linked list anymore when we're archiving because we're never going to append another object. So we can basically take the linked list and we just make it into a single entry array. We know exactly how many entries we need in it up front. So, and that basically saves us from having to jump around the file again when we're iterating over an entry array, because it'll all be in a single array without having to jump through the linked list. I didn't add slide for this, but another thing we did was add BetterFS compression for archived journal files. So because journal files and BetterFS copy on write don't really play well together when we're appending to the journal file, it's disabled. when we're writing to the file, but we didn't re-enable it when we were archiving the journal file. So I added that so that when we archive the journal file, we better fast compress it. And that led to a quite significant, I think, 10x savings. The compressed journal files were like 12% of the size of the original file. So that was also a very big saving. The 12% is without all the optimizations I did. After the optimizations, the result was a bit less. But that doesn't work on in-progress journal files, of course. So these optimizations are still useful for that case, and for journal files on file systems that do not support compression, of course. I think that was mostly it. Thank you, and any questions?
So the approach with the environment variables is certainly good for development and testing. But should I be? Oh, now this is better. Okay. No.
Go away.
So can we make it like, I don't know, something that if we do the rewriting of the files on archiving, and then look, for example, at the list of reuse of message fields and make a decision whether to build the like the additional data fields for that, or if the reuse is small, then skip it. And to restore the functionality that is removed by the lack of indexing. If somebody requests indexing, then generate an index on the fly and store it as a sidecar file. So that at least in principle, you get the same functionality but more efficiently implemented.
I think we could probably store maybe the list of fields that are indexed and not indexed. We actually do this in the journal file itself. But yeah, we would have to generate something on the fly, or maybe not even generate on the fly. We could, but we'd have to add special casing code to, even if something is not indexed, to still be able to find it using the same interface. Yeah, as provided by journal. Yeah, that could be something to add.
Well, how much difference is there to storing it in plain text? Like, let's say for a.
So without the optimizations, if I got a 70 megabyte log file, I got a 700 megabyte journal file. With all the metadata, yes. Oh, sorry. So the question was if that was with all the metadata included, and the answer was yes.
This is probably a stupid idea because I've never worked in this area, obviously. Isn't it possible to sort of have one bare bones log file and then like a basically separate log file with all of the additional metadata that you could later on glue together, for example, for archiving or whatever?
Yes, so I kind of considered that, but it's quite nice to have a single file. I think Leonard can expand on this.
So actually, when we originally did this is where we came from. We wanted to have a secondary index file, like mailboxes, for example, are commonly done this way, right? But the problem is, like, first of all, like the main file was supposed to just contain the syslog files then, but they are useless because we wanted to store all the metadata, right? So then you have to switch to a different format anyway, like JSON or something like this to be able to store the metadata. And then it just becomes very fragile because you, like, I mean, the writing model that we wanted is not to have locking, not to be able to rely that the system is powered off at arbitrary times. And this becomes a lot harder if you have two files to take care about that need to stay in sync instead of just having one.
MMap both like together.
Yeah, I don't know. We thought a lot about this, and then we.
This is fragile. Absolutely. That this is fragile. Absolutely. It's just yeah. When you really want to come down to cutting a lot of stuff out, like a lot of unnecessary metadata, then probably this seems like a straightforward approach.
but yeah, but coming like, of course, I mean, I'm always on board with things that basically are for free, right? Like for example, reducing the offset size. That suddenly, I mean, there's no drawbacks. I'm always more concerned about the other stuff where you actually lose functionality, right? Like it's hidden behind environment variables for a reason, I guess. But one more thing that I'm a little bit concerned about is like when we archive things for two reasons. Either because we reached the limits of the file or something like this and then decided, okay, we need to start a new one. That's like the clean path, but there's also, and that actually matters, and in some cases more than the clean path, is the dirty path, right? Like that the system has been aborted abnormally, and we come back and realize, oh, this journal file was never closed properly. Now we archive it, right? Yeah, I have a suspicion that this one is the case that that matters, right? Like because in many setups, it's actually you have more invalid, like non-cleanly shut down files than the other ones. But once you actually rewrite files on the object level, right, instead of on the byte level, you make yourself like you basically can't do this for corrupted files because of, or like incorrectly or not fully synced files because they are basically corrupted, and then you have a problem. So my question was, does that STD also have some format that can do basically what Btrfs like compression can do, which is like seekable compression? Does that STD have something for this? Because this sounds like the perfect thing, right? Like because you could do that independently of Btrfs, and you could do it with corrupted files and with regular files, and it just always works the same. And you would still retain some form of yeah. Because I mean, I think it matters a lot actually focusing on archive files, right? Like because I have the suspicion that most systems, I mean, I think in the default setup you have at least 4 archived files for one active file, right? Like so, compressing those much better, that would be. Yeah, but I mean, it always falls down if there's seekable ZSTD.
Yeah, it needs to be seekable. That's why I thought of the dictionary compression, is that you can do compression, but like not everything, so that you can still seek through the file. But it's not it's not an easy do it for the entire file.
I mean, there is another option, which is for some container images, there's a push because with ZSTD you can add like metadata sections and stuff like that. And I know that at least for container images, there is a proposal for container images to basically where you can seek out individual files by path name in a Z-standard compressed thing. And I'm sure that you could look at how that's done, and presumably you'll be able to use the same mechanism for this particular thing. I'm light on the details. I just remember that there is like a specific like metadata block you can add in the middle of a Z-standard stream, which you can then seek through some mechanism.
But anyway, the point that I was making is like I wouldn't spend too much time in trying. I mean, you're also welcome to do that on the active files. I'd always look at the corrupted files and figure out how we can save those things, because it's probably going to be the majority of data like that. And and it's a much harder problem, I think, like because once you do compression, then access always becomes slow. So figuring how to solve that thing.
Yeah, if only we could just compress the entire file and still have it work, but then it becomes a bit slow to all the rest.
Any other question?
By the way, just to mention this, the linked lists stuff, I mean, they are linked lists, all these objects, but they're also like, because every object is supposed to be double the size of the previous one, it's supposed to not be O of n, but O of like log n, the access time, because yeah, if you have a lot of objects, you have only a few elements.
I have a question. What's the status of this stuff? Are the PRs merged?
The PRs are not merged yet.
So are you waiting? Are you waiting for Mr. Leonard's blessing?
Reviewed it last week or something, like part of it.
Yes. So the PRs are not merged, but they have been reviewed by Leonard. So I need to address the feedback, and then we can hopefully get this in a release.
Okay. Any other question, comments? Anything online? Well then, thank you then.
Oh, if people want systemd stickers, you can come up and tell me what you like about systemd.
Testing the catch box. Yep, I see it in the room as well. Good. Good to go.
We use it. So, am I good to go? Is it time? No, I can do that, yeah. Okay. Hi. I'd like to talk today about secure unified kernel images for generic Linux distributions and everyone else. This is supposed to address something that for a longer time I think was solved pretty terribly on generic Linux distributions. And I think we should do something about this. So yeah, this is going to highlight some ideas, and most of these ideas are actually already. Oh, can I take this off? Yeah. Most of these ideas are also already implemented, so they're not just ideas. You still have to put all the building blocks together to actually get the result, and this is where there's still a lot of space to discuss. So before I start with all the stuff that I actually want to talk about, let's talk about what the status quo right now is. So the kernel image right now is typically on the big distributions, regardless if you use Fedora, RHEL, Ubuntu, SUSE, it doesn't matter. It's pretty much always the same. The kernel image itself is signed. It's built by the OS vendor and signed by the OS vendor. The initial RAM disk, however, is not signed nor encrypted and usually generated locally. Right, like you install the kernel RPM, and it has the effect of locally calling an initRD generator, and it generates an initRD and drops it into /boot. And yeah, that happens every time you update your kernel. It happens every time you have to change some basic configuration that affects the initRD, and so on. These initRD generators are basically every distribution has their own. SUSE has one, or I think they even actually switch to the one that Red Hat has. But traditionally, I mean, there are as many initRD generators as there are distributions. These initRD generators are usually shell scripts that try to magically figure out what actually needs to be in the initRD image and what doesn't. And the way they do this is mostly by parsing the output of LDD, right? Like look at the ELF binaries, look at the LDD output of it, and then figure out, okay, I need this library and this library. It's all a little bit black magic because this information is relatively incomplete. Like it cannot cover things like loadable modules, like for example libNSS stuff and things like that. So yeah, it's basically in a way it builds its own weaker form of packaging with dependencies and all those things on individual file level, even though most of the distributions have a package manager anyway. initRDs generally mix code and configuration. I mean, there's some certain beginnings of separating this because you have the kernel command line where you're supposed to put all the configuration, and then inside of the initRD you're not. But in reality, because initRDs end up with complex stuff, with certificates, with things like that, yeah, the initRDs actually tend to also contain configuration a lot. So it's all this fuzzy ball of everything that might be needed. Yeah, parameterization, I already indicated that this happens via kernel command line, and yeah, well, by including configuration files at the initRD image. Yeah, as mentioned, I mean, there are other ways how to do this, and there are certain systems that do it other way, but this is like, I'm trying to focus here on the big picture, how generic distributions do it, and I would like to propose how to change that. So the problems I see with this is, yeah, there's no integrity checking whatsoever, right? Like we have all this infrastructure for secure boot, but it only protects the kernel itself, not the initRD. It's the initRD is not protected in any way. It's trivial to backdoor the boot process of a generic Linux system because, yeah, the CPIOs, there's no protection, nothing. Every script kiddie can do this with the least amount of effort. Insert any kind of binary that gets started before full disk encryption is set up and can ask the secrets that it needs for full disk encryption from you, and you will have no way to figure that out. There's no confidentialities in initRD images, right? You want these too, usually, if you want, yeah, to have secrets, credentials for network boot and so on. Like you want to boot from iSCSI, and you need an iSCSI password for the things like this. Yeah, it mixes everything. So yeah, it's not very clean in any way. It's fragile because the way it's built, right? Like it's on the individual system, so it will vary widely between systems. And it's fragile because it parses LDD. It's a giant shell script that, yeah, might hopefully run, but also might be not run the way you expect. we nowadays want measured boot, right? TPM measurements, but that's all great if you can measure an initRD, but what's even greater is if you can actually pre-calculate what the PCR measurements will result in. Because why do you actually do the TPM measurements? Is because you want to be able to bind disk encryption to it or other form of security constructs to it. But if you cannot pre-calculate what the hash values will be, like the PCR values will be once you install this kernel and this initRD or something, it's very hard to bind stuff to it, because it basically means, yeah, you have to boot up, look at the values, then you can bind your stuff to these values, and then you have a problem when the kernel is updated or the initRD updated, because that means, yeah, you have to now recalculate the hashes and then update every single object you bound to it. And that's a mess, of course. So yeah, you want pre-calculated PCR values. Yeah, it's untestable due to combinatorial explosion, right? Like as we professionalize how Linux development works, we usually nowadays have large CI systems that try to really test as much as we can of all the components that we have. But this is almost impossible to do properly for initRDs, because there's so many options, and then you stick the configuration in it, and yeah. Yeah, and then, of course, also means that changing low-level OS configuration always requires to do a rebuild, right? Like, it's basically as if you're rebuilding your whole operating system every time you just make a tiny configuration to where you want to boot from. It also has its good things, right? Like, for example, it's extremely flexible and hackable. I mean, hackable can be a good thing, too. It's not just a bad thing if somebody can exploit your system. It's also a good thing because it's very easy. You just throw another file and rerun the generator, and there you go. It's typically more minimal than the usual package manager approaches, right? Like if you build the initRD from RPM, it's going to be larger, but yeah. And it's already implemented, tested, and deployed. So yeah, just so I wanted to just put this slide here basically so that people don't complain that it didn't have any goods. It has goods. So with the stuff that I actually want to talk about, these are the goals that I want to cover, right? I want to be able to pre-build initRDs that can be signed by the vendor, right? Like so that if Fedora wants to ship their distribution, they will ship it with one initRD that is pre-built on Koji, on the build system of Fedora, and similar for the other distributions. I want secure parameterization of kernels and initRDs, right? That we have a high, like that we can guarantee both integrity and confidentiality of the parameters we pass to it. This is, I think, this is a necessity because, yeah, we nowadays live in a world where you want to ship TLS certificates and iSCSI passwords and whatnot. So we should have some strategies there that even though we pre-build everything and make it immutable, we also still can pass parameters to it that are better protected than they are right now. What I also care a lot about is stable deterministic TPM measurements that can be pre-calculated. I already explained that earlier. Why that's a good thing. Yeah, I want still some degree of modularity, right? Like because if we pre-build them by the distribution, this of course, if you do it naively, it basically means everybody runs the same initRD, and that basically means everybody has to make the same choices on, I don't know, storage systems. Like everybody has to use LVM because that's what we built at the initRD or something, and so on. This is of course not going to fly, right? Like for a general purpose distribution, like Fedora, for example, is yeah, you probably want some modularity because people do crazy stuff in the with how they boot the system. So yeah, having a single initRD and that all would probably not suffice. What I also care about is kernel initRDs. I want as atomic single file updates, right? Like these things need to be invoked by the bootloader, loaded into memory by the bootloader, and it really is an interesting property if we can stick all these things into single files and update them as a single file, because that's as close as we get to atomic behavior, meaning that we can update a system, and because usually the file systems that the bootloaders read are bad, like VFAT, for example, you want to not stress the file system too much and make too many updates that are all required to compete before you can actually boot safely. So I want atomic single file updates, right? So basically, you drop one new file in there. Once you dropped it in there, you rename it to the file name, and that's it. That's the end of the story. That's your update of the kernel initRD and so on.
yeah, those are my goals, and this is how I intend to do this. Let's pre-build basic entities on OS vendor's build system. I mean, so far that I guess is obvious. Let's include them in a so-called unified kernel image, or UKI. Right, you put these components together and you sign them on the vendor systems all together as one. Then let's add an extension concept, because after all, we wanted a certain level of modularity, where we can add weird networking, weird storage, all the stuff that people want, without actually having to support that all in the basic itinerary. So yeah, that's this approach to deliver some form of modularity, not the same as before, but at least some. Then let's add a concept called credentials that allows secure local parameterization of unified kernel images. This is really about what I mentioned earlier, that we have authenticity checks and confidentiality to parameterize the initrds in a safe way. Let's measure these unified kernel images, like the individual components, into a PCR that is otherwise not used. PCR 11 I picked for that, because if it's otherwise not used, it starts with 0 if we measure our stuff into it, and we can calculate very easily what the value is going to be after the kernel has booted. Then let's also include a signed TPM2 policy for that PCR 11 in this unified kernel image, right? So you have now one single file that is protected as a whole through a secure boot signature that contains everything that you actually want. And when you boot it up, it will see you will see PCR 11 values on the TPM. And it will already have told you the ones that you will see, and you have a signature for them, and you can actually verify them. So yeah, there's going to be the next talk is going to be done by Zbigniew. It's going to be about building this basic itinerary, because that's an interesting question, like how to actually do this. And I already mentioned that the old ones had these generators, and it's all terrible. So this one's going to be much better. But yeah, wait for the next talk by Zbigniew. Let's go into a little bit more detail what unified kernel images are. So I already mentioned it's going to be a kernel image and an itinerary. But it's going to be a little bit more. So first of all, in the model that I envision, it starts with a systemd stub EFI stub. This is a little bit of a UFI program that runs in UFI mode. And that is basically what an earlier stage bootloader invokes. And then glued to this stub, you'll find the ELF kernel image. ELF kernel image is a bit of a, it might be misleading because it's also a PE image. It's kind of both. But anyway, this is the real kernel image that we're about to invoke. The basic initrd that we built the way how Zbigniew wants to build them. One fixed kernel command line is also baked into this. An etc.os release file. This is only for like earlier bootloaders to figure out what they're actually booting there. The idea is basically that the etc.os release file of the distribution this belongs to. SDBoot, like the bootloader from the systemd project, actually uses that to populate the menu to show you something useful, that this is a Fedora kernel that you're booting. Optionally, you can put some more stuff into it, like a boot splash, which is shown like it's put on screen before we transition into the kernel, right? Still in UFI mode, which is the good thing is that it's really, really early. You can put a device tree thing into it if you like. It's not my area of expertise, so I'm just going to quickly mention that. And then this, I briefly mentioned this already, that we can put a signed TPM2 policy into this of the PCR values that we expect once the kernel is booted. By the way, I know that I'm very quickly going over all the TPM stuff, and I guess not everybody here knows the TPM stuff so well, but it's just one facet of the TPM that I care about, which is about the measurements. And if you want to know the details, I hope you can look it up on Wikipedia. It's not that hard, and then have another look at that stuff. It's probably the easiest part about all the TPM complexity. Anyway, so there's another component inside of these unified kernel images are these PCR signatures. All that we combine in one single PE file. PE is the Windows executable file that UFI also uses, with a simple object copy invocation. Object copy is just part of bin utils. It's a way how you can add stuff to binaries, right? Like, so you basically take the stub, you add these things to the end, so that you now have a big file that contains everything you need. Some early UEFI boot code, the real kernel, the initRD, and so on and so on. Once you have the single file, you go and sign it with second boot, like EPE sign, SB sign, whatever tool of choice you want to do that. Now you have something that can be executed directly by the UEFI firmware. I mean, it's a PE binary like any other, and eventually we'll come up with a kernel. This can automatically be enumerated. Already mentioned that because the OS information is inside of that PE image, so it's very self-descriptive, right? Like simply by looking at that one file, you know exactly what you're actually looking at. Yeah. Further details on the systemd UEFI step. I already mentioned that's a small piece of code that still runs in UEFI mode, not in Linux mode, but in UEFI mode. What it mostly does, it sees that it has been loaded. It's a PE executable, and then just iterates through all the PE sections, like sections are parts of a binary, and tries to find these components. Once it found them, it ultimately invokes the kernel and the initRD with the kernel command line. That's kind of the key thing what it does. But before that, it can do other things, like trivial things like display a boot splash on screen, load the device tree thing. But the most interesting thing is, from my perspective at least, is that it measures the contained kernel and initRD into PCR11. I mentioned this earlier. PCR11 is otherwise unused. So by doing this, we have pre-measured basically what we're going to start. And then once it's started, we can look at the PCR and know exactly what's going to be in there. Something else that it does, it picks up credentials files from the ESP, right? Like I mentioned this earlier, that I wanted to have secure parameterization. My like the way how I think this should be implemented is via these credential files. Credential files are basically small snippets of data, or they don't really have to be that small. I mean, they can be certificates and stuff. They can be anything binary, anything text, and they can be encrypted and bound to the local TPM. It's authenticated encryption. With a symmetric key, and then you can put them, for example, in the ESP. That's one purpose, one place where you can put them, like in the EFI system partition. And systemd stub, when it still runs in UEFI mode, it uses the regular file system APIs of UEFI, looks for these, like just by looking in the same directory that it has been invoked from, looks for all these files that end in the suffix .cred, picks them up. And then, I mean, we'll talk about this later. Maybe I shouldn't mention this already. But basically passes it to the kernel. How it does that, we'll talk about later. It does something similar for initRD extensions. This is about the modularity stuff that I mentioned earlier, right? Like that we still want to be able to run not just with the basic initRD, but want to have extensions for them. So these can also be put in the ESP next to the kernel image and automatically picked up and passed to the kernel. Then what it also does is take this PCR signature from one of the sections and pass it to the kernel. How it does that, we'll see later. Yeah. So this is what the stub does. Now let's look at the extension images, right? Like the extension images are supposed to be like you have the basic initRD and you have a couple of extension images that add additional stuff like weird storage, weird networking, or what else you want. The idea again is that the basic initRD includes that is inside the unified kernel image is pre-built by the vendor and hence not extensible itself, right? You cannot locally insert stuff into that. So we added a concept to systemd a year ago, something that's called systemd sysext. It's a tiny tool, actually, that implements a system extension concept. Like primarily, we wanted to have that actually for the host file system, but we can also do that for the initRD file system. What it actually does, it just overlays a cryptographically secure disk image onto /user. Overlay means overlay FS. So the idea basically is you have the basic initRD, and then you have these images, which are basically GPT disk images with Verity and signature and things like that. These are, by this tool, systemd sysext, mounted, and then overlay FS inserted into /user where they can add additional files. I mean, the concept is that they're supposed to be additive, right? They're not supposed to replace stuff. You can do that with overlay FS too, and we will not block you from doing this. But conceptually, we want them to be additive, right? Like, so you have the base OS, and then you add on top the LVM files that you need through one of these extensions. You can use it any way you want, of course, but this is how I personally in particular intend this to be used. Yeah, I mentioned this. It works on hostOS and in the NRD. And these system extension images are GPT disk images. They implement a specification that we put together in system context, discoverable partition specification. It's basically, the specification just lists a couple of GPT partition type UIDs that have specific meanings. Typically, they would contain 3 partitions. One is the actual user file system to overlay onto the initRD. Could be squashfs, but we don't care. DM Verity data partition for this, and another partition that just contains the PKCL7 signature of the root hash as a DM Verity. When one of these images is activated, we just set up a loopback device, tell DM crypt, DM Verity that there's Verity set up, pass along the PKCL7 signature, and then the rest happens inside of the kernel. And then there it's even measured and whatnot. Yeah, it's not even we in user space who verify this. It's all done actually by the kernel itself. So it actually integrates with IMA and IPE and all these kernel level security frameworks that care for information like this. Yeah, mentioned this already. It's all merged into /user via overlay-fs, read only, purely additive, but this is not enforced. Yeah, this is not supposed to be package manager, right? Like package managers are traditionally relatively fine-grained. They're not as fine-grained as the initRD generators probably would like them to be, but they are still, not even supposed to be as fine-grained as package manager. So they are not supposed to be one of these extension images for each library or something. If you do that, I mean, you can do that if you like to, but I would strongly advise you not to. The idea is really that these add whole subsystem, right? Like that you have the basic one, and then you have one for LVM maybe, and one for iSCSI boot, and so on and so on. How this is actually implemented by the distributions, of course, entirely up to the distributions if they actually buy into this model. Version handling, because there's a question where we can do this right away.
Hello, I have a question. So these extension modules are signed also by the vendor, or?
Yeah.
Okay.
So the idea basically is that these extension images are built at the same time as the initRD themselves are built, at the same time as the kernel is built, and they just are not installed by default, except if you actually want it. So it's not supposed to be a package manager again, right? Like, and because of that, there's also really no version handling. Right, like there is no, I need this specific kernel version at least, and this one at most, or something like this. We don't want dependency how stuff and not replicated package manager. So all it does basically, there's a system extension API level, and then you say, okay, this is for kernel number 77, API 77, and then, or initRD 77, and then that's it. And how you upgrade that level is entirely for you, but it's supposed to be linear and simple. But again, this is for the distributions to figure out how they actually want to use this. This is just how I say how this should go. So how are these extension images picked up by the kernel when booted? I mentioned this already, that the system destub is supposed to search for these files in the ESP directory where the image itself is in. It loads them then into memory and generates on the fly CPIO initRD image from them. Because not everybody knows this, but the kernel actually is happy to accept as many CPIO archives as you want. You can just concatenate them. CPIOs are an extremely simple format. I mean, there's a reason why the kernel picked that format for the initRDs. So we can actually trivially easily generate them also from that system destub UEFI stuff. So this is what it does, and it puts them in one fixed directory, and /.extra.sysext. It basically, this makes sure that we can use the ESP UEFI firmware drivers to still load them, and then in the initRD, they're just that.
So I have a question. The .extra directory, as I understood correctly, it lives on rootfs, right?
We're talking about the initRD, right? Like, so the initRD is run in a tempfs ultimately these days, even though we.
Okay, so .extrafs directory, it lives in the initRD image, let's say.
Sorry.
So if you put
Yes.
sorry about that. So the question is where the .extra directory lives, in initRD or in rootfs file system?
No, I mean, they're supposed to contain information about how to find the root file system. So if we would put them there, that would be defeating the point. So they are copied.
Maybe I misunderstood. Okay, okay. Sorry.
They are just one CPIO init or D.
Okay,
like
okay.
any other, and then they are all unpacked one after the other by the kernel. So they are just in the tempfs that is the.
Oh, okay, got it. Thanks a lot.
So systemd_sysx then looks into that directory and picks them out automatically, goes to the kernel, sets them up, kernel verifies everything, all is good, measures them, and so on. And there you go. Now we have a /user file system that has both the basic stuff in and this extension.
Quick question: is the last point actually true?
No. So it's
because
like systemd_sysx exists and it does things. What it doesn't.
But it
do
looks
right
in
now,
varlib. It doesn't look into that place.
It currently actually doesn't look into that directory.
Yes.
The reason why it doesn't look into this directory right now is that it's like we cannot trust the stuff that is in that directory because it comes directly through the ESP, right? We must establish trust first. And sysx right now trusts everything it sees, right? So what's still missing in sysx is that when we read the image from that directory, we must insist that it is Verity enabled, right? And that part is still missing. It's a tiny bit of policy check extra, but yeah, good point. I mean, most of this exists. Let's say 93%, but there are still gaps. Let's talk a little bit about parameter. There's a question.
So it's still a question on the previous one of extensions. So how do you measure the extensions? So you must measure them as well.
So we don't. We leave that to the kernel really right now. Like there's IMA, but I'm not sure. Like I don't have a practical experience with that because I never actually used IMA myself. I just know that people do. But sysx from user space will sort the images and execute them in alphabetical order to make the measurement stable. But right now the assumption is that the kernel does that and we don't.
I mean, you couldn't extend the systemd stub to enumerate and measure PCRs into PCRs of all of those files if you really wanted to.
This was the incomplete answer. I would expect that IMA will eventually measure this, but also systemd stub measures them also into another PCR. So systemd stub actually not only deals with PCR 11, it also has PCR 13 or something that is otherwise not used, where it measures system extensions into, and then there's another PCR where it measures parameters like kernel command line and the credentials too. So you have your choice basically from 3 PCRs, like one is the kernel itself, one is the system extension images, and one is everything that is parameters. And it's up to you how you bind your policy together. But again, I still think, like, I mean, it depends what do you actually want to measure. Do you want to measure all the stuff that was passed over, or do you want to measure the stuff that was used? I have the suspicion in many cases that's the latter thing, right? But I mean, how distributions end up implementing this is up to them. By default, the like disk encryption policies are something that bind to TPM that we also ship in systemd that don't care about either of them. Like it only cares about the kernel stuff so far.
Things like command line and changes to init-RD, they can be sensitive from security point of view. So that's why it's actually important to measure everything.
Yeah, we do measure everything.
Yeah,
like
and that's enough, and then everyone can do.
If you look in the man page that we have about this, it actually measures like, because different parts of the system measure different things to different PCRs, there's a massive overlap. So there are actually some resources that are measured 4 times into 4 different PCRs in effect. I put a table there actually because it's very confusing, the fact that everything is measured so many times. And it basically tells you for every resource what you can pick there. I think we now have individual PCRs for the relevant stuff that I personally would at least bind stuff that you can pre-calculate.
I think you might have already answered this, but are you taking into account? I mean, because that's a lot of PCRs. Are you taking into account like how to actually upgrade individual components without changing too many, just because of
So it's a good question actually. Maybe I actually have a slide about this, but I already mentioned this. Is like the model that I'm following here is not so much that PCRs are what policy is bound to, but that signatures of PCRs is what policy is bound to, right? So the TPM actually is happy to verify for you that the TPMs are in a specific state if you give a signature along with it, and the public key that belongs to that signature was enrolled when the disk encryption was done. So this is a different model. So how most of the distributions, whoever did TPM stuff, implement this, because it basically means when you update your OS, you don't have to re-enroll, right? Like because it's up to you now to, like, the vendor can simply, because everything's pre-calculatable, it can pre-calculate what the PCR value is going to be, and then the results it can sign and put in the UKI. I mentioned this earlier in the slides that there's a section to put the signatures in. And this is what is then used and basically relieves us from having to re-enroll and everything, because the idea of re-enrolling on system updates, because all the TPMs change every time again and again, that might work if you only care about a root file system and nothing else. But I think there's more in this world than root file systems. We want to encrypt credentials, for example, which are just files somewhere in the file system, and bind them to the TPM. And we cannot possibly, just because we update the kernel, go through all possible files in this world that were ever encrypted like this and re-encrypt them basically with a new key. So one of the key models here really is, of the key design points, is we don't bind policy to hash values, we bind them to signature hashes for the PCR stuff.
The PCRs are just measuring the hash plus signature, or what? What is actually going?
PCR, like the PCRs are measured, like the measuring process works the same as always. However, if you then have a secret key you want to lock against them, you don't lock against the literal values, but against the signatures of values. It's like, you know, secure boot, right? And
Yeah,
secure boot, you
fine,
can
just making sure I
enroll
understand.
hashes, you can enroll signatures, right? We do the exact same thing for PCR. It's it's the way how I think the TPM stuff should be used, but it's not how most people, like most implementations so far, do. I mean, I know that some people do, and probably behind closed doors people do, but yeah.
On the chat, someone's asking, where is the kernel getting the credentials to verify the Verity signatures?
The Verity signatures, like, I mean, the credentials to verify the kernel. Like,
the public key is baked into the kernel itself.
Exactly, that's the idea. That you know, kernel modules need to verify, system extensions need to verify. You need to verify lots of things. The idea is that you always bind it back to the kernel as much as you can, and because the kernel is secure boot verified, this is your hook. How you then yeah, put everything else on. Okay, so I still have some slides. By the way, we don't have to go through all the slides. I think, like, the basic concepts I already explained, but I'm actually really happy if there's a discussion going on. I much prefer that of just going through my slides. But anyway, if nobody has a question right now, let's continue with the parameterization. So in a secure boot environment, passing parameters to the kernel is problematic if done without authentication, right? Like, because, for example, if you have a kernel command line option and you use it to turn off some security feature, SE Linux equals 0, then you have compromised the system in a drastic way. So yeah, in secure boot environments, at least the way I see them, kernel command line is locked down. It's in the model I mentioned earlier that it's included in the unified kernel image, and you can't change it without making the system unbootable. Now, so what do we do instead, right? Sometimes we need to pass information after all, iSCSI information, networking stuff, whatever else. So how do we do this? In system, we have this credentials concept, as I said, but it's very hard to authenticate and do. I mean, it's not impossible, but it's nasty to authenticate and decrypt them already in UFI. So because that basically means if you do something complex as that, you basically have to include a TPM stack and OpenSSL pretty much in the UFI code. I mean, shim embeds OpenSSL, but I'm not sure if that's something we should repeat. So we'd rather avoid that. So we came up with the concept of credentials. The idea is really that credentials are authenticated and decrypted the moment they're used, not the moment where you pass them somewhere. Credentials are something that we added to systemd originally. They are service credentials, so it's the way how you can pass parameters to system services. But we all extended the model to also have something like system credentials that you pass into a system. Originally, the systems you could pass them to were basically containers, like systemd endpoint containers specifically. Yeah, we made this possible that you can also pass them into anything else. Like, for example, you nowadays can pass them in from a VM manager through something like SMBIOS type 11. Not going to go too much detail there. But yeah, so there are various ways how you can pass these bits of information that are potentially authenticated and encrypted into the system. Here, we added a new one so that you can actually source them from the ESP. The data that's included in service credential is really up to you. It can be anything, really. My assumed use for it is identity information, server information, certificates, key material, passwords, and things like that. Yeah, when you pass them to the system, they're system credentials. Credentials can be encrypted and authenticated. We use AES 256 GCM. By default, they are encrypted symmetrically and authenticated symmetrically by a key that is the combination of something that is locked to the TPM and in the local file system. Yeah, I talked earlier about how the EFI stub stuff picks up the system extensions. Exact same way it picks up the credentials and puts them in a CPIO. They can then, once the system is booted, they're just there, and you can propagate them down to services. Many system components support them, but we keep adding places where you can add them, because for us they're more than just something we can use in the context here of booting and parameterizing a physical boot, but we can also use them to as a cloud init replacement in a way to provision information into virtual machines and things like that. From it, by the way, like how does the API look like from receiving side? Yeah, if you have a service, you just get an environment variable called $credentials directory, and you read them their files. That's that easy. The service receives them unencrypted, right? And if namespacing allows it, only they will see them and nobody else on the system. All this happens in user space. Anyway, I only have less than 5 minutes time left, so I'd rather switch to using that for question than for the rest of the slides.
The first question, I think this is quite an interesting idea. Sorry, but I have a question. Do you see any problems with implementing this approach in other bootloaders than systemd boot? Is anything in this implementation which relies on systemd boot specific? No.
So everything that I was talking about is SD stub. So systemd has SD boot and systemd has SD stub. The boot is just a boot menu. It's not even actually a bootloader. And all the stuff about the credential stuff is and the system extension pickup and the PCR stuff that is implemented in the systemd stub thing, which is its little glue program that you glue in front of it. But any bootloader can invoke that, right? Okay. It could be grub or whatever else. However, it expects a relatively complete UFI environment to be useful, right? Like, for example, if it shall pick up the system extensions and the credentials, it needs file system API on the image that it's loaded from, right? I think this is what, for example, grub currently doesn't do that, right? Like it gives you a file handle that isn't actually, there's no file system behind it, right? Like,
So I understand that you are saying that if we call the systemd boot system stub from the grub directly, it will work. Okay, this is obvious. But if you want to implement the functionality of systemd stub in the grub, it is possible. Doesn't this functionality rely on anything specific? Okay.
I mean, a systemd stub is a trivial piece of code. Like, I mean, it does number of things, right? It measures stuff. It looks
like an I understand that.
Like, it uses the TPM APIs. It generates CPIOs. It does. That's nothing fancy.
Okay. Just asking.
It's
Thanks a lot.
Piece of code.
I mean, in Ubuntu, we do boot systemd stub with grub with just exec space, blah blah blah.
But we are loading EFI stuff. So you are loading EFI stub binary from the grub using chain loader, right?
Chain loader. Or
Okay. Okay.
Sorry, just one quickly. You mentioned that the command line is signed and you can't change it, but then I had the impression that you were about to say how there is a way you can modify it, but I don't see that here. It's just not possible at all.
Well, so I mean, this is an issue that comes up, this entire ideas have been circulating for a while, right? Like, and this is an issue that it comes up all the time because people love changing the kernel command line. So I personally do not do that very much, right? Like, I know that people do that. I know that people do this, but I think if you change your kernel command line, you're a hacker, right? You're not a regular user. And that's, if you then turn off SecDebug to allow this, then that, I think it's fine. That said, people have been asking for this all the time, and this recently came up in confidential computing context, where people asked, they don't actually care that they want to change the kernel command line freely. They just want to have the ability to choose from a couple of okay choices, right? For example, they want one that indicates debug boot and another one that's factory reset boot and things like that. So we discussed this as an RFE in systemd, and everybody agrees how to do this, that we just going to allow that you can embed in a couple of other more PE sections that just encode, oh, by the way, this is also a good configuration where you pass, where you define a fixed command line, give it a name, like an identifier and a pretty name, and then sdboot, for example, looks at this PE section and looks at all of them, and then it finds like 7 different configurations are supported and generates 7 boot menu items from them, and that's how you support them. But I know that people want total flexibility, but I mean, you have to make compromises in life, right? Like, you can't give people the ability to turn off all the security features because that's what the kernel command line does if you want to enforce security. Like,
yeah, I mean, I was about to just give the example of the debug mode in systemd, whatever, which is in the command line. But if it's one of those things where you can pick from a certain set, then for most users, that's probably enough. That's, yeah.
Exactly, right. Like, and then the distributions would have the freedom to pick as many different sets that they want to support, and then anyway, this.
Yeah. So, question regarding the extended modules that you're talking about. So the flexibility here will be laying for the vendor. So the vendor will choose what do they think the user will need, and they will create these extensions. You won't give the ability to the users to be able to load their own.
Well, you can do whatever you want with this, right? Like, is this just like the model that I have in my head? I'm not even a distribution vendor personally. It's like use it the way you want. This is all new stuff that is not widely deployed. Some of it are more widely deployed than others, but you know, to make this very clear, I don't intend this to be another package manager, right? This is the. It's good to know what you are, and it's also good to know what you really don't want to be. And I don't want to be in the business of being RPM. So that's why I underlined this. But then again, it's free software. You use it for whatever you want. And if you want to come up with a model where third-party people can generate these images, knock yourself out, I have no problem with that.
Just it comes to the point of security and verification. In this case, if I'm allowing users to do that, like, for example, the third-party kernel modules, like X drivers for specific vendor, won't be signed because it was in the kernel. So the user, the only way is either to sign their own images from everything for kernel graphs and everything, or just
ask questions.
So let's maybe then go to one of the last slides.
No, let's go to Zbigniew actually, because we're out of time.
That's the questions.
Okay.
Regarding the credentials thing, how would the user go on to sign it if I want to use it for something like Cloud Init replacement or whatever? Those are user controlled values, right?
So I mean, if you want to use it as a replacement for Cloud Init, right, you run it in a VM environment, for example, or in a container environment, then there is no encryption or authentication done in this case usually, because why would you if you can trust the hypervisor? The model that we recommend for this, and that is already implemented, is you use for VMs, you use SMBIOS type 11 objects, which is like, they have existed for a long time. They basically allow the firmware vendor to put there anything. In QEMU and in Cloud Hypervisor, at least of two of the VMs, you can just specify this on the command line. So the idea basically is, yeah, this is then put into some memory that the firmware announces is there. This shows up in /sysfs in /sys in some directory, and system just finds it there and uses that as stuff. It's the best way how you want to provision your VMs, because it's ridiculously fast and extremely user-friendly, because you just add it to the QEMU command line. All the other stuff that Cloud Init was network and what the stuff that came before it, like with CD-ROMs and whatnot, that's all terrible. This is what you want to use. Actually, we're trying to convince all the cloud vendors. I mean, I work for one of them, but try to convince that everybody just implements that, because it also gets rid of this need to have some vendor-specific network protocol or something. Because, I mean, it's not really standardized for this purpose, because the SMBIOS spec says can be anything, but it's effectively standardized because we say, yeah, and systemd reads these strings and makes use of them.
It's also way faster, like we found out. If you just, for example, use Cloud Init to enroll, like, I don't know, an SSH key and the root password, you can, if you do this with the systemd credential through SMBIOS, it's like, the numbers were like half.
So it was 18 seconds to first boot an Azure VM, and it was my laptop 4 years old. It was 4 seconds instead on QEMU.
So yeah. Anyway, if any one of you works for AWS or some other cloud vendor, please just implement SMBIOS 11 support, and then once you do it, then everybody else does it as well. Okay, I'll pester him with this stuff, but yeah, because I mean, this Cloud Init stuff just needs to die. But yeah, I think Zbigniew, you're on.
Okay, thank you, Leonard.
Welcome.
So,
Is this on? Yes.
My mask there somewhere.
Nope. But can I make it full screen? Because it's like okay. So my name is Zbyszek, and I'm part of the systemd crowd, and I'm going to be talking about the distro part of this whole new design for boot issue. So Leonard's talk was like an intro, but I was making the slides yesterday before midnight, so I had to make up some quotes like a good journalist. So that's what I thought that Leonard would say. And so this gives the technical approach to how this is all put together. But I want to talk about the more social part of how, as a Linux distro, you can actually make use of this and to generate all the necessary bits without going crazy. And I want to mention some things that weren't mentioned before, some goals. So we want to have reproducible builds. I mean, I believe that packages should be designed in a way, or package build systems, where you can rebuild everything a second time and get bit for bit exact result. And of course, reproducible builds of initRDs are part of this. And to not go crazy, I mean, this adds a lot of complexity. If we don't want to go crazy, we have to remove complexity just so that the system is more manageable. So the current approach that we have, it is a design that was driven by requirements of 10 years ago. The primary thing is that the initRDs that we generate are supposed to be fast because they must be copied or unpacked on every boot. And this is, I mean, CPUs are slow. They were even slower in the past. If the initRD image is large, it takes forever. Everybody wants them to be small. So, well, at the time, sysvinit was, yes, there's a sign from the back. Oh. At the time, people were well using sysvinit, and you couldn't put sysvinit into the initRD. So lots of custom stuff that did some event-driven logic and minimalistic boot systems were created. Yes, question?
Well, actually, more of a correction. I was around when the event-driven Drake was written, and the goal was not necessarily speed. The goal of being event-driven was getting rid of crazy stuff like sleep 5 while we wait for a disk to appear.
There were a lot of sleeps in the old days.
So, sure. I mean, okay. No, I mean, maybe it's like my post-facto interpretation, but well, I mean, the flexibility, versatility, and choice were also considerations, and because of the way that we boot the way that we configure the initRD, we can either put stuff on the kernel command line or in the initRD itself. So, well, I mean, this gives certain characteristics. So everything must be done locally. There is just no way around this. There is, I mean, we end up with custom scripts and custom implementations anyway. And because of all that, the environment in which the scripts are running or the programs are running is very special, or used to be very special. And as Leonard mentioned quite explicitly, I mean, we repeat the work that the RPM or Deb is doing or whatever. And at least in many, I mean, not in every distribution, but in Fedora and optionally in Arch and in other places, we use both something special and systemd. So we kind of have, I mean, two things that want to be unique together. And all this complexity isn't really necessary anymore. We can just let systemd win. And we spend a lot of time on every end-user machine during every kernel update, and this is also painful because it's often the most noticeably slow part of an update. So the kernel does not care. It is just a temporary file system instead of a file system backed by a device. There are some tiny differences, like the kernel will start /init instead of /sbinit, but I think it's just a historical accident. So, right, I mean, if I want to convince Fedora to use this, I want to reuse distro packaging. I want to use systemd to the full possible extent, and also use normal daemons that I would install in the real system in the initRD. To a large extent, we end up doing this anyway because, I mean, who is going to re-implement LVM or other stuff in the int_rd. I mean, this is just a waste of resources. And once systemd is doing the setup, the int_rd looks almost the same as a normal system anyway, so there is no point to do something different. And we can just use normal things, and those things can expect a completely normal environment with /proc and /sys and everything being present. The whole thing shouldn't explode in size, so it can be a bit bigger, maybe 2 times bigger, 3 times bigger, but not crazy. Yeah, it should be reproducible. Then we can build things centrally, save cycles. Then we can sign them, and we retain flexibility by building system extensions, and this can also be done centrally. Of course, we have to sign those too. Everything is supposed to be signed using the same keys. And kind of as a social aspect of all of this, right now, if a user reports a bug that happens during early boot, the maintainers of the int_rd packages have to look at the bug and figure out, is this specific to the int_rd builder? Is it part of the int_rd runtime that is very special, or is it maybe a bug in some other component? And this creates nobody wants to look at those bugs, and they just pile up. So the idea is that we will build the int_rds and a number of system extensions. I'll repeat this because I think it's a bit tricky. So the int_rd is a compressed CPIO archive, and each system extension is delivered as a GPT image with the file system, a partition for the file system, a partition for the DM_verity data, and a partition that contains a JSON file that has the signature for the DM_verity data. So it's a bit too, I mean, it's not completely trivial to generate this, but it's also not anything particularly complicated. And of course, the kernel understands this natively and can make use of it without, I mean, the user space just passes the image to the kernel that gets mounted as a loopback device, and we are, I mean, you can use it directly. So, for example, it's a common request that people want the SSHD to be started in the int_rd if the root file system cannot be found, so that you can connect to the machine and debug stuff. So I can imagine a system extension with something that brings up the network, starts SSHD, maybe some other stuff. For example, in rescue mode. As mentioned by Leonard, I mean, all the non-standard storage for the root file system would probably live in some extension. I think that we also want to bring up the full graphical stack in the int_rd. People might consider this crazy, but there are good reasons. Right now, if you're a visibility impaired user of Linux, well, I mean, the full story is pretty sad, but in the early boot phases is especially sad. If we want to fix this, we have to be able to bring up, well, graphics. This also works for internationalization. We need to display fonts, and well, we cannot do that on the console. For similar reasons, we probably want to bring up the sound stack. Right? I mean, if the machine is supposed to talk to you, not to show you pictures, then well, we need this, and we need Bluetooth to connect to the speakers, and maybe also Bluetooth to connect to the keyboard. And I think at this point, pretty much all of the distro is potentially included to be run in the int_rd, all the basic components. I'm not saying that we should do this by default or that we should do this in every case, but that it should be possible in an easy user, in an easy way that is chosen or not by the user. And I'm sure that there will be more ideas. So the the implementation. Make operating system image, MKOSI, is a program that is used to build images from packages, so more something that we want to do in this case. It is designed to take a list of packages, build an image out of that, then take sources for some program, install this onto this image, and generate this final image out of this, and well, boot it up for testing or whatever. In the case of the initrd, we don't care about compiling anything from sources. We just want to take a list of packages and build the initrd. We started using MKOSI for this because it already has support for the stuff that is relevant, so GPT tables, Verity data, signatures, and it supports creating of archives. So CPI archives were easy to add. So MKOSI uses the distro package manager to do the installation of packages. So it's actually a fairly simple program. And because we use DNF and apt and so on, we support all the common distributions, and it's kind of easy to add new ones. Fedora, CentOS, RHEL, Mageia, OpenMageia, Mandriva, all are covered by RPMs, and Debian Ubuntu are covered by Deb, and so on. And there's even some support for Gentoo. And the build process is parameterized by some configuration files and some trees that will be inserted into the image, and a set of scripts. So tweaks can be done to the build process. And what is fairly important is that MKOSI supports incremental builds. So you do a build, and then you do another build starting from this point. And this is quite nice for building the extension images, right? Because the system extension image is a upper layer in an overlay FS. So you build the image to create the initrd, and then you do the build again with the extension contents ending up in a separate layer that then is packed up as the system extension. And MKOSI writes a manifest, so just a JSON file that contains a list of all the installed packages and their versions. And build reproducibility is being worked on. It should be available shortly. So the project to actually build the initrds is called MKOSI initrd, and it's just a few config files for MKOSI. When we started working on this, I expected that this would be a lot of work, but it turns out that this is like the minor part. The big part is tweaks in all the tools and systemd itself, and integration of system extensions with other tools to make this all easy to consume. So MKOSI has a list of packages, and a finalized script to do like the few tweaks that are needed to turn an host system image into an initrd image. It's really just a few files, and a set of configurations to how to build system extensions. This is, this part is mostly something that will happen in the future because we're still fighting with the basic system. And of course, if you build this, right now we're not doing this centrally as it is planned in the future. We're building things locally, and it also means that you want the build to happen automatically when you install a new kernel, and we have some integration with the kernel installer that is invoked. So for example, if you install that in Fedora, you basically will get a image built by MKOSI initrd on the machine after a kernel upgrade. So I guess it's even slower than the current approach, but in the future it might be faster. The part that is missing, well, I mean, the technical implementation at the low level is there, but we are missing integration with the distro. For system credentials. So, for example, there is a request in Fedora to be able to authenticate users when the initrd tries to boot and cannot boot properly against real user passwords. So the idea is that we would take a list of users that are in the wheel group or have administration privileges, and we will create a system credential that contains this the details how to authenticate those users, encrypt it using the TPM so that it cannot be read easily from the when the machine is offline. And then if the boot goes wrong, then we can use this to securely allow administrator users to get into the initrd. Right, I mean, we need less things because things are just too complex. In this scheme, we let RPM do the heavy lifting or deb or whatever. We don't duplicate packager work. We don't take files from the host, we take them directly from packages. Every package has a signal, contains hashes for the for all the files, so we know that the stuff that we are putting in the RD is what we expect. And then we can actually have images that are reproducible when they're built, and what is even more important, they're the same for everyone. Because right now, well, a user reports an error in the initrd. Can we figure out what they are running? Kind of, right? And then, right, we can sign the images, and we can use systemd to do the heavy lifting. So it is already doing that in, for example, in Fedora, because it is already present in the initrd. So we just remove the duplication. And I mean, it's always better to use the host implementations than to the custom replacements. And since the initrd is now like any other system, I mean, it's very similar to a container system that just doesn't have too much stuff running. It is much easier to ask people to work on it because they don't need to learn a new special thing with special bash scripts doing special things. And like at the distro level, this is important because it's easier to direct bugs to the right place so that they can fixed. Well, a few years ago, we went through this transition where different distros ditched their custom init systems and, well, customized init systems, and people kind of settled on systemd. And I hope the same can happen for the initrd. Basically, just maybe there's some splash file that you'd insert, but otherwise everybody could use the same. Well, that's what I have. Questions, comments? Please go ahead.
Thanks, by the way. I apologize if something that was covered maybe in the previous talk, but I wasn't there. One of the big issue we've seen at AWS with the initrd to the system transition is the fact that we do transition between effectively two environments. So systemd rigs itself, we have two libcs, we transition over. And that transition has always been racy. And the more things you add now to the initrd, the more hardware management stuff you're going to add to it, the more we're going to have problems transitioning from that initrd environment into the final operating system. And I wonder whether it's worth starting to think through maybe a world where instead of transitioning, we extend. And so the components that were started from the initrd remain, and we just, through either links or overlays or whatnot, and bind mounts or whatnot, extend the initial system rather than complete transition. Because we still have chasing a race today, I believe, in systemd around
block device detection during the Unitary to OS transition. We've papered over some of them, but
so can I answer?
Yeah.
So in this case, we are certainly not using a different LPC or anything else, right? We want to actually use the exact same things.
No, it's still a different instance of it. You're restarting
different version. Yes.
You're restarting systemd. You're going to have to restart all those hardware management daemons, your Bluetooth things. You're going to have to do that whole OS transition.
Yes.
And that's very hard to get right.
Well, I think that
you're not going to get it right.
It
That's
must be gotten to get right, because you want to restart services. All services must be restartable during the write-up of the system so that you can do upgrades. I mean, for me, the idea that you require a boot to change your, I don't know, Pipewire instance is just not feasible. And I think it becomes much easier because this transition from the interd to the host requires some serialization of state, but the serialization of state is exactly the same or very, very similar to the serialization that happens when you restart the service. So I think that if you can get the latter right, then you can also get the former right.
Everybody's right.
So in a previous slide, you mentioned Gentoo, right?
Yes.
Yeah. Actually, coincidentally, there's a Gentoo developer in this room, and that's me. So I was a bit interested and curious about the use case you have in mind when mentioning Gentoo on that side. I see probably Gentoo doesn't belong in the same ballpark as the other binary distros.
So the case for support for Gentoo in MQSI is because people also want to use it, right? I mean, also want to do the same thing for program testing and stuff like that, and image building. For the interd, I have no idea if this will be useful.
Actually, it might be possible to integrate portage with the new initrd generation way, because portage could be used to build packages and install into an alternative route, and we could actually build stripped down versions of a package with like a use flag, like use equals to initrd and etc. So it might be actually possible to somehow integrate this idea with a Gentoo approach and philosophy.
I mean, we use portage, right?
It might be interesting.
So I guess it will be just a question of adding support on the package side in Gentoo.
Yeah, send us pull requests. We're happy to have them. I think it was you first. Oh, go ahead.
I'll use this one then. Just coming back to your idea about not doing a full reaxec, but just adding in basically the root files and stuff. This certainly can work, right? Like, but it can work in a scenario where people use, for example, Verity for the root file system anyway, right? Because the initrd is basically immutable. I mean, it's actually not, because it's a tempfs, but it is effectively immutable because it's But I think in an environment where you have Verity, it definitely makes sense to just overlay this and then have basically just put the main operating system in the initrd, and then instead of the initrd actually finding the real one and reaxecing to it, it would just basically merge a big extension into it. That's totally doable, but I wouldn't call that an initrd in this way. There is no initrd involved. It's basically just a system that as a whole is embedded into the kernel and then happens to activate one massive system extension, right? Which I think, I mean, it's an attractive model. I'm totally not against this, but in generic distributions, and I think this to some degree kind of focuses on that, like on Fedora or something like this, it's unlikely to be what you will deploy because, it's not. Yeah, but I like the idea. Like it's certainly something to think about. I mean, in systemd, it's not entirely easy to do it like that, because in systemd, once you drop in a couple of services or something like that, you probably want to activate them, and the way how you activate them is by starting a transaction. And so the model currently is that
yeah, we at early boot we figure out what that transaction is and then we stick to it. And here you would have to issue at least a reload to systemd itself, not a reexec, but a reload, so that it then afterwards can like see the new units that appeared, come up with a new transaction, merge that with the old one. So that's
It's
you can do
doable.
this. There's nothing wrong with it, but
I mean, it's just an idea like this, just food for thought.
but I like the idea, but I see problems. But it might certainly
because we
be
do have
something.
problems today. I mean, I believe you were just telling me before, somebody else there, that, for example, Ubuntu does not use an itild on AWS for that specific reason. The difficulty of transitioning is real, and yes, we could just fix it, but clearly we haven't. And I think the more we would want to add services, especially hardware-related services, the more we might be fighting an uphill battle. I might just be pessimistic. I apologize, but it has been in the past, at least, a real issue.
But I mean, yeah, I sympathize with the idea. So
I think it was.
Yeah, I mean, in some way, right now we're at this phase because there have been so many ideas how to do the TPM measurements and which PCRs to use and what to put where and in which way. I think that we are in the phase of building the tools, and the actual policy that we will end up using in the end is very hard to predict at this point.
I have a comment from the chat. I'm not convinced we should do this, and instead we should maybe look into an init-rd-less system.
Well, I mean, if you have complex storage and you want to have encrypted credentials, then and a system without an init-rd is hard to make. It's hard to make it do those things.
Dan was first there.
So I was wondering how in this model, how hardly is the kernel still coupled to the init-rd? Do you still need to rebuild the init-rd on every kernel
Well,
update?
if you extract the modules into a system extension, for example, then possibly you wouldn't have, but then you would need to make sure that everything that is necessary for the kernel to load the initial system extension with the modules is built into the kernel. So yes, I think that not rebuilding at least most of the init-rd for new kernels would be nice, but I mean, I would leave it for later.
And maybe one other question is, how often when you're building the init-rd in the well, in as the vendor in Koji or whatever, how would you rebuild it on every package update that is included into the init-rd?
SUSE, yes. Yes, other people not.
Well, I would build it when building the kernel, so you would get like a new, just repeat the current system, so you would get a new one every 2 weeks or so. I don't see why it would be so important to update for every kernel package unless you have an important bug.
If I have one more question regarding this systemd reload from the init-rd. What are the issues with that? If you were to say, like, okay, you start the systemd in the init-rd and then mount your real root possibly into user and then do systemd daemon reload, what would be the problem with that, with keeping the systemd in the init-rd instead of re-executing it?
The initial point wasn't about the systemd itself, but about, for example, some daemon to manage RAID or something, that it needs to seamlessly transition to a different copy, and the state must be propagated.
Oh.
And especially if it's something about networking, for example, then there can be a lot of state, right?
So basically, I mean,
just to respond to you as well, systemd does still have races and doesn't get that right in a number of cases, unfortunately. I mean, we're trying to fix them, but yeah, it's yeah, but really hard, really hard one to find and to solve. Like it's really not trivial.
So
because you have all those kernel events coming at the same time during the transition, and yeah.
So doing just the daemon reload is much like, I mean, it's really supposed to really just work and not create issues in contrast to the reexec, like the switch root thing. But still, I advocate that that daemon reload should be kept out of the boot phase as much as we can. Is my current thing, because it's slow, because there are some things where we cannot sanely catch up if they happen while we are restarting, because restarting takes time, and there's a lot of shit happening during boot, like UDEV stuff probing and things like that, and we try really hard to catch up afterwards, but this is only working like this. Yeah, as mentioned, there are races. It's like
it's a really hard problem.
it's a very hard problem, and so generally my solution is, if you can at all, you just have the initial system be running all through the end, and it's the one that originally figures out the transition method.
So what?
Yeah. So you mentioned the special MK ISO initrd, where you were working on trying to use MK ISO to actually build MK OZ, I mean, to build initrds. It sounded like you already are sort of using that, since you also have the kernel install hook.
So we are using it on our laptops, and
Yeah.
it mostly works.
How big are those initrds?
So they're bigger because the kernel in Fedora has all the, well, not, it has, there are kernel modules extra, and kernel modules something, and I just take the first package and extract all the modules from that and put it in initrd, and this is about half of the initrd, because I don't want to bother with selecting the specific. But if we ignore this question, it's 20% larger than the drop.
And I would guess you also get a lot of Linux firmware there. You need Linux firmware if you want to bring up the GPU. Or are you just not bringing up the GPU yet?
Yes, I'm not sure about this. I put in some firmware, but probably not all of it. I don't know.
Right, because that's very big too. So, but so they're working on splitting that though. But we probably need like one extension per GPU, like an AMD GPU extension, and.
Christian, go
ahead. So how far away are we from a distro actually switching to this at some point?
I think that if we told distros to switch to it, it's technically feasible, definitely, and it would work for maybe 50% or 80% of users, maybe even. But the remaining integration pieces would cause such a massive
for NVIDIA and whatever this is, yeah.
So I think for real, it's time to work. I mean, we should talk about this when it's like 99% ready, as far as we know, and then we can, like for example, the firmware cases, they need to be covered.
But I think I'm asking an annoying question. What I mean is, there some sort of time frame? Do you have any idea when you want to, for example, try and get this into Fedora, which I assume?
No, I don't have a timeline. I don't. Michal, do you have a timeline?
No, I don't have a timeline because so first maybe to Hans, like the fact that these initrds are bigger just means we have a lot more work to do on a packaging side. Because if you think about it, LVM, for example, like now with MKOSI initrd, we take the entire package, but what LVM Dracut module does, it's sort of like second order packaging, right? Like it extracts the core of LVM, which is usable to bring up root file system, and we need to make that package as a sub package of LVM, same for everything else. So that's the work that we need to do on the packaging side. And regarding what you asked about, like how close are we to use it in Fedora, I think that's the most difficult part, is try to figure out like what's essential, and essentially first work on getting rid of Dracut modules. Essentially, we need Dracut modules which have module setup.sh, and install section just installs plain RPMs, essentially just contents from the packages. Right. And that's the first step. Like once we get there, we know we can convert it to this and it will work.
So the nice thing, I mean, because there has been actually many small tweaks done in various places for this, and I did a lot of work on tweaking various packages to, for example, reduce the dependency set, also systemd. And one of the motivations for dropping GNU-TLS from the default linkage of systemd is that. And The nice thing is that whenever we do that, we actually benefit other cases, like in particular containers. And
yep, very much so. Congratulations for Untitled, by the way. We've been trying to get rid of that for container image for a while. Couple of things, just a quick response to the Fedora case. If we really have to, we could imaging adding some kind of RPM environment global that says that you are in that context and have the install section do different things. I mean, sub packages is probably nicer, but if we have to, we can go down that path. One thing what mentioned earlier about kernel modules versus this, they can, and they probably should be disconnected. It would be nice if the MKOSI bothered about the user space and the kernel install could install the necessary pre-signed extension with the necessary drivers so that they can just be collated, especially in a context where we might want the initrd to be signed, and in a context again of secure boot and all that jazz. Food for thought.
So quick partial answer. To a large extent, this is already possible because we already collect system extensions from per kernel version location and a global location. So the idea so far was that this can be used for example, for credentials which are applicable to kernel independent, but we can possibly move most of the initrd if it's like a separate thing into this layer.
And again, I missed the previous talk. I will watch it later, but I don't know if the system extension can just be appended physically to initrd. That way they get loaded by the firmware, which solves the problem of requiring the drivers to load the system extension. And then they get separate signatures. They can be separately verified. I don't know. Food for thought, the kind of thing we can look into. Because we really want to get to a world where the initrd is signed. And we do not want private keys, even in a TPM, to exist on individual, especially in the cloud, on individual instances. So we want things signed on our build systems and immutable from there on. Just thoughts I've been having.
Yes, so we see the signature living in a for the initrd, at least in the unified kernel image approach, the initrd and the kernel are together and have a signature. Yeah. And for system extensions, the signature is also embedded, and it's all verified by the kernel. I'm not sure if this answers the...
I will have to watch Lena's talk.
Any other question, comments? Anything on the chat?
Well, time's up, so.
Well, thank you, Zbigniew.